Okay, it is exactly 1:30, so it is time to begin. If everybody could take their seats, please. And I'd like to welcome everybody to the 40th anniversary celebration of CIMMS. I'm Greg McFarquhar. I've been director of CIMMS for the last year. So we have a bunch of presentations for the first couple hours here, and then we'll move into a poster session. And this is meant to celebrate all of the accomplishments of CIMMS over the last 40 years, and also to describe a little bit about what is to come in the future. So I'd like to start by acknowledging part of the CIMMS leadership team. Randy Pepler is the Associate Director, Tracy Renke is the Executive Director of Finance, and Sebastian Torres is the Assistant Director for NOAA Relations. And what I'd like to start is to give you a bit of an overview about what exactly a cooperative institute is, for some of you who may not be familiar with that, and more specifically, what is a NOAA Cooperative Institute? Well, a NOAA Cooperative Institute is basically an academic or nonprofit research institution that conducts research that supports NOAA's mission goals and strategic plans. So what we really do here at CIMMS and all the other cooperative institutes do is we create a long-term and meaningful collaboration between NOAA laboratories and universities. Part of the way of doing this is to provide NOAA sponsorship of students through fellowships, and in doing so, we help to educate and train the next generation of the nation's scientific workforce. We are not the only cooperative institute. There are cooperative institutes all across the United States. So you see here CIMMS, we're in central Oklahoma here. There's also cooperative institutes in Washington, California, Oregon, on the East Coast, Colorado, and so on. And all of them are charged with different goals. But they all relate to NOAA's mission goals. And the 5 primary goals of NOAA are healthy oceans, weather-ready nation, climate adaptation and mitigation, resilient coastal communities, and NOAA enterprise objectives. And the work we do at CIMMS, it could probably fall under all 5, but the 3 which we most emphasize are weather-ready nation, climate adaptation and mitigation, and NOAA enterprise objectives. And probably our most prominent goal that we contribute to NOAA is through the weather-ready nation. And NOAA's mission goals within the weather-ready nation are to improve weather decision services and to deliver improved weather forecasting services to support management of the nation's water supply, to improve sector-relevant information in support of economic productivity, to integrate environmental forecasting services, and to sustain a high-skilled professional workforce with training, tools, and infrastructure to meet the mission. Now, we, of course, do not provide the weather forecasting services ourselves, but rather we do a lot of research on ways to improve the methodology of doing these weather forecasts, and we work to transition them to operations. In terms of climate adaptation and mitigation, the goal of NOAA is to improve the scientific understanding of the changing climate system and its impact. And here within CIMMS, we would spend some time looking at extreme weather and how some of these extreme weather events may be changing in an evolving climate. And in terms of NOAA enterprise objectives, for those of you who aren't familiar with that, it's really functions for engaging partners and customers, or the underlying administration and management functions that support NOAA's work. So in terms of a CIMMS overview, Jeff is going to talk more about the history, but we were established in 1978. We're the largest and second oldest research center at OU. We're a center of excellence in mesoscale meteorology, weather radar, and regional climate to produce better forecasts and warnings to save lives and property. And what we have to deal with phenomena that are on very different scales. So we have to worry about the scales of cloud nuclei, which can be on the fractions of micrometers, and we have to go all the way up to synoptic scales, which are thousands of kilometers. And we also have a wide variety of activities. We deal with observations. Eric will later talk about field projects. We deal with analysis and modeling, understanding, and prediction of weather elements. And one of our last talks will be Kim, and she'll talk about some of the increasing emphasis we have on societal aspects and socioeconomic impacts of such phenomena. In terms of highlights, last year we had $19.1 million in expenditures. The bulk of that was from NOAA through the cooperative agreement, but it's important to note that we leverage those NOAA funding and that we get funding from many other agencies such as the state of Oklahoma, the Department of Energy, NASA, and the National Science Foundation. By latest count, we have 196 people. Actually, I think it's now 197. Of those, 130 are staff, mainly people with masters or PhDs in atmospheric science or a related field. We also have a large student presence. We have 34 graduate students in CIMMS, 32 undergraduates. Last year, we had 119 peer-reviewed publications, 62 of which were led by CIMMS scientists. And we have a lot of scientists who work in other activities as well, what's called R2O, or Research to Operations. And we also have some who are doing training, involved in training activities as well. So in terms of today's agenda, we're going to hear about some of the activities that are underway in CIMMS. If we have 196 people in CIMMS, I hope you understand that you're not going to learn about everything going on in CIMMS today. But we do have about 70 or 80 posters outside during our reception where you'll be able to get more details, take a look at some of the projects that most interest you, and some of the scientists will be by their posters to better explain some of their activities. In terms of what we're going to present today, during our oral session, we're going to talk a little bit about the history of CIMMS. Then we're going to have talks on radar meteorology and radar engineering, as radar has been one of our main focuses over the last 40 years. We've also had a big emphasis on storm scale meteorology and forecast and warning improvements, so we'll have a couple talks on them. Then we'll talk about CIMMS' role in field experiments, and we'll finish up with a talk on societal impacts, and then I'll try and guess a little about what the next 40 years hold for CIMMS, because I sincerely hope that I'll see you all here in 40 years for our 80th anniversary celebration as well. So that's a challenge to everybody in the room, okay? But I'm going to stop here so that we keep on schedule. But before we start, I'll give an opportunity if anybody has a couple of questions before we start. You can raise your hand, and we have people that will run around with microphones if you have a question. Okay, if not, we're just going to get into the talks then. So we are going to start with our first talk, which will be by Jeff Kimple. Jeff earned his bachelor's degree in psychology from Denison University and his master's and PhD from the University of Wisconsin at Madison. Jeff is also a veteran of the U.S. Air Force, and he was awarded the Bronze Star for meritorious service in Vietnam in 1967-1968. A few other things about Jeff. He was the Associate Dean of the College of Engineers, the Director of the School of Meteorology, the Dean of the College of Geosciences, and the Senior Vice President and Provost of the Norman campus. He's also retired as the Director of the Federal National Severe Storms Laboratory, and he retired in 2010. I should also note that he's a fellow of the American Meteorological Society, and he's also past president of the American Meteorological Society. So given how long, given his great service at all the different, sorry, that slipped out. Given his great service in all these different roles, I thought he'd be the ideal person to talk about the history of CIMMS. So Jeff, welcome.
Thank you, Greg. What Greg mentioned was I have a hard time holding down a job. So what can I say? If nothing else from my talk, I want you to remember this bridge, because that's what CIMMS is. It's a bridge between the University of Oklahoma and NOAA. Without one of those entities, it would be a bridge to nowhere. So you've got to have both connected by the 3 C's of the Weather Center, which is collaboration, cooperation, and co-location. Those are the 3 C's that built this place. Before I go on, I just want to make sure everybody realizes what a great deal cooperative institutes are. They're probably one of the most symbiotic organizations known to humankind. Because if you think about it, having a cooperative institute in Norman at the university invests millions, hundreds of millions in academic programs that are relevant to NOAA. And the university invests hundreds of millions of dollars in educating students that are employable by NOAA. What an amazing arrangement NOAA gets out of a couple $1 million, what did I hear, $19 million investment in CIMMS. What does the university get? The university gets expertise residing nearby. The university gets adjunct faculty that teach some courses. I'm amazed that some of the forecasting courses at the graduate level in the School of Meteorology are actually taught by some of the best forecasters in the world at the Storm Prediction Center and the local Weather Service Forecast Office. And students are employed, graduate students are supported, and that little $20 million deal, and that's the record, by the way, in the history, and you look in the past, it wasn't always like that. So I just wanted to point that out and say it's a perfect symbiotic relationship. So how did CIMMS get started? It's kind of a fascinating story because it's related to the other CIMMS. The CIMMS at University of Wisconsin, the Cooperative Institute for Satellite Service, Meteorological Satellite Services. And what was going on in 1976? Well, first of all, the first Cooperative Institute was CIRMS at the University of Colorado in 1967. But in the mid-70s, Bill Smith was a NOAA employee in Washington, D.C., and he had a group of satellite people that he was talking to Vern Sumi in the Space Science and Engineering Center at the University of Wisconsin, and he was going to move them to Madison, to the beautiful Space Science and Engineering Center building, 15-story building, and then create a cooperative institute to facilitate interaction between those two organizations. Well, Rex Inman talked to Bill, and Rex didn't have to move anything because Ed Kessler and NSSL were already here. So even though the idea germinated with CIMMS in Madison, Wisconsin, we actually beat him to the punch and established the other CIMMS in Norman in 1978. And it wasn't until 1980 that the other one was established. So Rex Inman, who was the chair of the meteorology department, Ed Kessler, Rex becomes the first director of CIMMS in 1978. It's hard to find a picture of Rex. It was pre-internet, but there is one. He was the CIMMS director from 1978 to 1980, followed by Yoshi Sasaki from 1980 to 1986. Both of those were in the old building, the old engineering laboratory building. Look at the radiator behind Yoshi Sasaki. That gives you some flavor for what we were dealing with. Now, how many of you here were students in the old engineering laboratory building? Those were the good old days. Okay, you can remember that. Doug Lilly took over in 1986 until 1991. We'll talk about that, and then Pete Lamb came in 1991 until he passed away in 2014. I really want to give a shout out to Randy Pepler, who was the interim director for 3 years. I think that's probably the record length of being an interim director in any organization that I'm aware of, and he kept the place together, he kept the trains running on time. And now we have, of course, Greg McFarquhar, who's been here for a year, and we expect great things from him. In fact, Yoshi, Doug, and Pete were all George Lynn Cross Research Professors, the highest research honor that the University of Oklahoma bestows on a faculty member. Now, I also wanted to put up here where the CIMMS offices were located, but there's not many places left where they were. The original one with Rex and beginning of Yoshi was the old engineering laboratory building, a building so old it was built before electricity, an engineering building that was so out of touch with the world that it had no women's restroom. But that all got fixed, of course. Yoshi moved CIMMS to a church, a repurposed church that unfortunately was on the corner of Boyd and Jenkins, the southeast corner, and got Res to build the Energy Center. So Doug moved CIMMS to the Drake building on the other side of the railroad tracks to the east across from the Mont, and it got Res to build this very odd apartment complex that's wedged between the railroad tracks and the gas station, but still has easy access to the Mont. But I didn't put pictures of those. I didn't put pictures of those up there because they're gone. Now, also, Emily, I want to thank you for, I don't know where she found these ancient pictures out of newspapers or Sooner magazine, but on the left is Rex Inman, the second picture that I'm aware existing of Rex, with Peter McDonald, who was an OU graduate, but he was the chief of the Navajo Nation. And so here's Rex showing him the Norman Doppler, the beginning of everything radar in Norman, Oklahoma. And on the right here is Doug Lilly and Yoshi. Look at this, with an Apple IIe and floppy disks. Now, I know there's people in this room that have no idea what those are, but let me tell you, at the time, they were state of the art. So, Steve Koch, I want you to tell us who the first 3 CIMMS employees were.
Oh.
That's you, Steve Koch, right?
I was one of them.
Yeah.
I was one of them. Carrie Emanuel was the other. And the third was... Hello, I'm Steve Koch. I was one of them. Carrie Emanuel, who went to MIT afterwards, and then Steve Bloom, who went to Goddard, and I went with Steve in 1980. I was a 1-year postdoc at CIMMS in that old church building at the corner.
So we had 3 famous people started off at NSSL, and it only got better from there, right? Just kidding. The research themes. The first 3 on the list here are pretty much the original research themes for CIMMS: weather radar, storm scale and mesoscale modeling, and forecast improvements in research. And when Pete got here, he expanded CIMMS into 2 more areas: climate change related to extreme weather events, and also socio and economic impacts of high-impact weather that Kelvin Drogemeyer picked up from, it was a national priority from the National Science Board to link science and people. And I'm really happy to say we've got a very good program spinning up here in Norman, in CIMMS, in that important field. I have no idea why I did this, but I'm going to do it anyway. And this is actually on-the-job training for Greg. Being in this job, you never know what's going to happen. You never know what's going to come out of left field, and you never know what's going to take time away from your research and your students. But think about this. Here's a SMART-R radar. It was a shared resource involving CIMMS between OU, NOAA, Texas Tech, and Texas A&M. Who buys the insurance? Who does the insurance cover? Who can drive the truck? Well, believe it or not, we actually worked out a thing. It took us about 2 years, and then the administrations changed, and when we went to renew it, they said, no deal, you got to disassemble everything. That took a lot of work, and I'll just say, things like that happen all the time. Feds who had CIMMS people working for them used to evaluate them and send them in to the university, recommend raises. evaluate their performance. We got a no from Department of Commerce attorney. Oh, the worst thing that can happen as CIMMS director is you pick up the phone and it says, "Hi, I'm so-and-so, attorney from the Department of Commerce." Or, "I'm so-and-so, I'm legal counsel for the University of Oklahoma." When that happens, you know it's going to be a bad day. That's all I can say. We used to hire CIMMS people to do everything with computers, from high-end computer programming to doing all the IT support. Well, we got challenged by some private companies, and we had to give that up. So now we have multiple IT companies. But the good thing was we were able to preserve the high-end computing, the scratch computing, the scientific computing in CIMMS. And we have a lot of good people there now. The biggest one, the one that I remember the most, is we got a renewal, a 5-year renewal, and attached to it were special ward conditions. And the ward condition said you can no longer do anything in CIMMS with weather radar. Think of that. I mean, that was kind of our bread and butter at the time. So Pete and I went to Washington, and fortunately we had the support of the AA and the deputy associate administrator, and we got together with the lawyers. And I was so proud. You can have good bosses. That happens sometimes, just so you know. And the lawyers said, well, not only can you not do radar research, you can't do anything useful to NOAA. I can't make this up. They lost a legal case about digitizing strip charts. And the DAA, Louisa Koch, I'll never forget, she just stood up. She said, out. Get out, to all the attorneys, and all the attorneys left. And somehow it all got worked out. I have no idea how she did it, but that got fixed. Pete also had this wonderful idea for a logo. If you look at the logo in the upper right, the white is a U, the red is a O for OU, and the blue, and the seagull is NOAA. Well, we got a call from the attorney on that. Turns out the NOAA portion, the seagull part in the ocean and the atmosphere are trademarked, and we had to take it off. However, there are times when CIMMS does work really good. When we were script consultants for the movie Twister, we had worked out a deal with Universal Studios. By the way, the NSSL logo was developed in concert with Universal Studios, and it's also trademarked. And the deal we had with Universal Studios was they were going to put it on everything they sold, coffee cups, hats, shirts, and we were going to get 7% of the gross to spend on research at NSSL. Well, the lawyers went nuts, you know, and so we had to add, if you look in the bottom, that U.S. Department of Commerce, National Oceanographic and Atmospheric Administration to the logo, and we got a call from Universal Studios. Jeff, you know we're going to embroider those. We're out. We're having our own logo. Goodbye. But the good thing was that they said, we want to honor the contract. We want to give you the first year of our estimate of what the funding would be if we could keep this deal. So we tried to give a gift to the federal government. Let me tell you, that doesn't work too well. So we went in and we said, you know, a lot of CIMMS people had a lot to do with helping this, the Twister thing and building the Twister attraction at Universal Studios in Florida. You could give it to CIMMS. So they gave, I forget, it was $50,000, $60,000 to CIMMS, went in the foundation, and it bought one of the trucks under one of the SmartR radars. So CIMMS are very useful in that regard. Very important, 2 major organizations were born out of CIMMS. When Doug was the director, he wrote the proposal for CAPS. CAPS was a big deal. Kelvin Drogemeyer was the co-PI, and NSF about had a hissy over one of their premier science and technology centers was run out of a NOAA Cooperative Institute. So what we had to do is we had to dissolve that relationship. Doug moved to the Center for Analysis and Prediction to the CAP side, left CIMMS, and then we hired Pete Lamb to replace him. So that's why that transition happened. While Pete was coming in, a very interesting RFP came out for the Department of Energy Atmospheric Radiation Measurement Program, which was measuring clouds to try to improve cloud modeling and climate models. So Pete actually wrote that proposal when he was still in Illinois, but we knew he was coming here. We'd already hired him, and so he came and caught that proposal. Very quickly, because I'm running out of time, it's amazing to me the growth in CIMMS. I mean, here's just the last 10 years. It grew from roughly $10 million to $19 million. The blue is the support from NOAA. So most of the support comes from NOAA. If you think where it started, this is huge. And the other thing that's very interesting is the number of students that are supported by CIMMS. Graduate students over the last 5 years have been about 30, the lower 30s. That's about a third of all the graduate students in the School of Meteorology. But look at the undergraduates. Undergraduate students can work in NOAA part-time, roughly 40 each year can get support toward their education. So wrapping up, 40 years. Steve Koch said there were 3 employees. Now there's 195. I got this information last week. I've been corrected. There's 197. So 2 more people have been added in the last week. So the growth's still positive. That's a good thing. 40 years, annual expenditures rose from a couple $100,000 to $19 million. If you want to know the value of what you get from a research organization, multiply it by 10. A research grant can be $1 million over 5 years. What's wonderful about CIMMS is support comes every year. $19 million a year, every year. So over 10 years, that's $190 million. That's real substantial funding for the programs here in Norman. Currently, 12 NOAA and 6 CIMMS scientists are adjunct faculties. They supervise graduate students. They teach courses. And I will just, the other thing is federal scientists can submit proposals through OU. That's how essentially our lightning program got supported every year, Don McGorman, Dave Rust. And I will just submit that CIMMS is the heart of the Weather Center because it draws NOAA and OU together. I'm in trouble. You said I'd be in trouble if you stood up.
I said when I stand right beside you.
Okay.
Sort of
okay, everybody else can relax. All the future speakers can relax. So that's it. Any questions? No questions?
We've got one right here.
Oh, there's
Sebastian.
another one back there too.
Oh, one back there. Okay, here first and then back there.
It's Jamie.
Okay, hand one microphone to Sebastian and then take the other one back there. Okay, go ahead.
Thank you, Jeff, for a great presentation. I wanted to ask you if you could give our young scientists at CIMMS a piece of advice, since you've seen and lead so much.
You know, the younger CIMMS people have a way of burrowing in, finding very interesting and important things to do related to NOAA, work with their supervisor, and I can't tell you, there's another graph I wish I'd put on here. How many CIMMS people have been here more than 20 years? Plus, how many CIMMS people have transitioned to federal positions, and how many CIMMS people have transitioned to faculty positions? There is a path into more permanent employment if that's what you're looking for. But you can really have a career in CIMMS. And the other thing about CIMMS is that as opposed to being a Fed, you can consult. So a lot of people want to be in CIMMS and they don't want to be Feds. So.
Does someone have their hand up?
Okay.
Okay, well, we will Okay, thanks again, Jeff, for a great presentation. We will now move to our next presentation. Our next speaker is Dr. Pam Heinzelman. She is a research scientist with the National Severe Storms Laboratory, and she has 20 years experience in the areas of weather radar, severe storms, and warning and forecast applications. She is a former employee of CIMMS who transitioned into NOAA. And in 2016, she moved from the Radar Research Development Division to the Forecast Research Development Division to serve as the Warn-On Forecast Program Manager. And now this summer, she became the Division Chief of the division. So she is also a winner of the Presidential Early Career Award for Science and Engineering, and she's going to talk a lot about the radar meteorology work that is going on in CIMMS. Thank you very much, and that has gone on as well.
Thank you. It's my pleasure to be up here, and I wanted to kind of set the tone for what do I mean when I say radar meteorology. And so I have a basic definition up here. So radar allows us to observe the atmosphere, right? So we're talking about the environment as well as storms, and then using that information to make predictions, whether that's in a nowcast sense or also with models. And what you see here is essentially a radar history of the development that has happened within Norman, starting with the NSSL Doppler, followed by the Cimarron dual polarization radar. So that was the first one developed by mostly NOAA folks, I believe, at that time. And then that was followed by the KOUN radar, which became the kind of the prototype for the upgrade for the National Weather Service. And during that time, also, we started developing Doppler on wheels types of systems, because with the systems we had developed before, of course, it depends on the storms coming to you. And sometimes you want to take yourself to the storm. And so we see a number of instruments there, some of them done in collaboration with the university, I think all of them done in collaboration with the University of Oklahoma. And the beauty of being able to take them to different places is that we can observe phenomena that may not be as frequent here, such as that windstorm that you see there, and the storm that was sampled, storms that were sampled in Colorado. You see the mountains and perhaps some snow in the background. And I understand that work done there has recently resulted in the production of a new radar site in Colorado. So what an exciting outcome from that. And then going to the Blue Dome, when that was painted blue, it's a phased array radar dome. We got a lot of feedback from Norman, the city of Norman. Didn't necessarily like that, but it's withstood its time, and started with a SPY 1A system that was there and that I worked on with several other folks for several years, and has recently been replaced with the Advanced Technology Demonstrator, which Sebastian will be talking about. Some people like to see if they can barf or not on an airplane, and that would be people who get on the P3. And that would not be me. My stomach couldn't take it. But that is another important, we have radar instruments on that, on the front and in the back, that collect very important observations. Terry Schur is one of the CIMMS folks out there who has spent time on that. And then, of course, we have CLAMPS, which is related more to looking at the environment itself. Okay. So I thought we would start with a little bit of fun, okay? I had not put together a word cloud before, so I wanted to learn how to do that. And what I did was I took all of the papers that CIMMS authors on them that were on the NSSL website that had to do with mobile radar. Okay, and so that's where this word cloud comes from. And so mobile is really big, but I thought it was interesting. We also see lightning is showing up here quite a bit. We've got dual, and that dual goes with Doppler. It's not dual pole yet, but that dual goes with Doppler. And I think it shows that there are a variety of storm types and integrated work that goes on in the field. It's not only about the weather radar. This is what you get if you take every single article that has the word radar in it that also has a CIMMS author within it. And so now we see some other themes that are starting to show up. We see polarimetric in big letters. We actually see row HV shows up. I thought that was kind of cool. ZDR, and we also see Zernich. Okay, so lots of interesting names there. I would say the number of articles, like, it was so long, it took me forever to get all that text and put it into this. So there's been a really high number of papers that are related to radar with CIMMS authorship. So Jeff just talked about the history, right? And one of the things that's a challenge is that, you talk about the folks who were here early, like Steve Koch. If you go back and you try to find a paper that says CIMMS in the authorship during that time, it's impossible, right? They're not out there. I think one of the first ones I found actually had Eric Rasmussen on it. But there were a lot of postdocs and students and things like that that were supported early on. And in the research that I did, what I found was that the installation of the 88D network was really a kickoff for CIMMS development, the CIMMS scientists that have grown over all this time. And of course, that happened in the late 80s to the early 90s, and that was around the time that I started my career. And what was great about that is instead of having just a few radars here and here, now we have this national network from which we can draw data at a number of different phenomena in different geographic regions and things like that. And the National Severe Storms Laboratory received a gold medal for that, and I bring that up just because it's a good thing, okay? So that is really the kickoff, and like I said, one of the first people I found as an author was Eric Rasmussen, and you'll see on the diagram in the middle there, he has all these radars that are WSR 88Ds. And the paper I'm referring to there was written in 1994. And within Vortex, of course, they were bringing in other radar instruments, those trendy cars with instruments on top, or geek mobiles. Some of you may have gotten to go in a geek mobile with what's his name? Bill Paxton, right? So he actually came out and was on one of those chases with us. But all these different radars that have evolved over time have allowed us to go out in the field, make observations, learn more about severe storm processes. And so this is a sampling of different titles from papers that have used weather radar in that capacity, and we see a really nice diverse set of topics, again, from lightning to bow echoes, of course, supercells and tornadoes, as well as work along the dry line. And this is just a small sampling of what those look like. Okay. So the next person that I found, who's a key person who's been around for a while in the mid-90s, was Alexander Ryzhkov. Okay. And why do I bring up him? Because he came on board at the time when the Cimarron radar was being developed, and he was brought on to, I see him as really kind of the start of deep learning and investigation of what we can do with dual polarization radar. And he did use that system to do the work that's shown here. A lot of the early work was focused on how might the data from a dual polarization radar help precipitation estimates. And so the diagram that you're seeing here, the bottom line message is that if you use KDP in your radar rainfall estimates, instead of only Z, you end up with more accurate rainfall estimates. And the reason for that is the ability to not gain information not only about the size, but kind of a medium bulk volume size, but then also the distribution or the number of drops therein. It ended up being the precipitation estimation, being able to do that better, was really the reason why polarimetric radar ended up being sold. Okay, so that's what brought about the transition of polarimetric radar to operations. And this is just a diagram showing the performance of the polarimetric algorithm versus a conventional algorithm with radar estimates from a special network that was in Oklahoma. Okay, but there's more. Okay, so we not only got better rainfall estimates, but we got hydrometeor detection. And it's not only hydrometeor detection. Here I'm showing in the middle, of course, perhaps the more sexy part is being able to identify hail, rainfall intensity. Of course, we've gone from that to tornado debris signatures, as well as ZDR columns and all other kinds of fun signatures that are interesting not only from a process perspective, but from an application perspective. And I'm sure that Don will be talking about that in his presentation. And of course, it's not only about severe weather, it's about winter weather and being able to see transitions and bright bands and going from rain to snow and things like that. And then, of course, there is our improved data quality. And that's from the ability to identify things such as biological scatterers, so insects versus birds, and also AP, for example. So we can have cleaner data. And why does that matter? It matters not only for the meteorologist and for finding the signal that you want, but also for the use of the data in numerical models. Okay. So this collaborative work between folks at CIMMS and NSSL resulted in yet another gold medal. Okay, and this was in 2014 for developing and implementing dual polarization technology that then was an upgrade that occurred across the United States. This would not have happened without the cooperation between NSSL and CIMMS. I would say it was critical to that. Okay. So now we're going to move on to talking some about phased array radar. And this is a picture of the group that worked on the development of that system and got it up and running and then started working with the data. And we see Doug Forsyth there in the middle, who was the leader of our group, the Research Development Division. And he always liked to put R2D2 on the slide, RRDD. You get it? Okay. So I put that on there in homage of his leadership. But again, here we're looking at a group of both NSSL and CIMMS researchers working together. Okay. Two of the major questions that from a science perspective, that radar meteorology perspective that we looked at were twofold. First, how does the rapid adaptively scanned radar data improve the understanding of severe weather processes? So I'll show some examples of that work, as well as then how can this information, if number one is true, be used to produce more accurate and timely warnings? Okay. So here's a subset of papers, and if you know some of the people on this list, you'll see we've got postdocs, we've got some students on that list, and I just wanted to bring that out just to bring forth the point of the importance of CIMMS in bringing students, postdocs, and folks like that, kind of rejuvenating, and building the workforce. I think that's really important. So you see a whole slew of papers here, and I don't want to talk about any of those in detail, but this talk would not be the same without a radar animation. So on the top, what you're looking at is 26-second observations through a hailstorm versus 5-minute observations. And these are actually both from the phased array radar SPY 1A antenna. So this is a totally fair comparison, I guess, kind of. But anyway, you can see a lot more of the detail, and that's what we were looking at, from a process study perspective. Are you seeing information that is being missed. And I think in this case, that's fairly clear. We see much better the development of the Hale core. We know it's significant due to the 3-body scatter spike, etc. So that's just one example. Here's another set of papers that gets more on the application side in working with students with forecasters in the test bed and seeing then what does the usability of that look like? Can we improve warning performance? Can we improve the decision process? And that's what these papers looked at. And here, let's see if I can get it to play. So I had to show not only a vertical cross-section, but I had to show a PPI, so we can have equal time, both for Hale and rotation signatures. So here we're looking at circulations actually from, this was just before Erin. How many people were here during Tropical Storm Erin? Okay, there was some hands in the room. So we had these low-top supercells that occurred prior to that, and these are some data that we collected during those storms, and this is also one of the cases that we used with forecasters in the test bed to look at the utility of the data. So what did we learn from all this kind of in a nutshell? Well, we learned that the data we were using, which was mostly 1-minute updates, provided more detailed information about storm processes that advanced scientific understanding, check, and also improved what we learn about improving forecasters' capabilities using the data, situational awareness, ability to make mastery decisions, performance in terms of severe and tornado warning lead times by several minutes, also improvement to POD reduction in FAR. So we had some really good findings there. And finally, I couldn't end this presentation without talking about how radar matters for war-on forecasts. And this is one example of that, where we're looking at the probabilistic QPF with radar data and no radar data. And this is work by Nusrat Youssef. And we can see the black contour is the stage 4. And we can see a big difference in terms of where the probabilities and the high probabilities lie with respect to the stage 4 with the radar data and without the radar data, as well as the improvement in the fractional scale score. So radar data matters. Okay, so I was also asked to talk a bit about what's next. And of course, the next big system that we have available is the Advanced Technology Demonstrator. And Sebastian, I'm sure, will be telling you more about that. But based on my experience, one thing that's for sure is late night data collection. Right? So that's where we kind of get to play like a forecaster and be up late at night and put in a lot of hours collecting important data sets. And then, of course, there's a science component. And my intuition tells me there will be a lot of focus on the microphysics and microphysical processes. Now we have more rapid updates with the dual polarization data, and so a focus on those. How do they relate to storm dynamics, thermodynamics, and specific hazards? And then finally, hopefully with any new system, it's great to have a surprise discovery. So perhaps something that we don't even have on our minds right now will be found, as well as, of course, the development of QC, so we can do observational and numerical modeling studies. Forward operators for dual polarization parameters, that's really starting to kick off now, and it would be great to be able to use some of the data from this radar in that capacity, as well as visualization, and probably, you might want to think about a new acronym instead of PRECE. Okay, so that was the acronym that was used for all the experiments we did with forecasters, and I will leave that up to the new group to decide what they want to call that experiment. Thank you.
Okay, we have time for a question or two. You made a convincing argument. Okay, well, to stay on time, we'll keep moving along then. Our next speaker is going to be Sebastian Torres. He received his bachelor's degree from the National University of Mar del Plata in Argentina and his master's and PhD from the University of Oklahoma in electrical engineering. And after that, he joined the CIMMS, and he's now the assistant director and a senior research scientist and the coordinator for NOAA operations. He's affiliated with the National Severe Storms Laboratory. He's received the 2016 Dean's Award for Outstanding Service, the 2011 Department of Commerce Gold Medal as a member of the Radar Research and Development Division at NSSL. He's also an adjunct faculty member in the School of Electrical and Computer Engineering and a graduate faculty at the Advanced Radar Research Center at the University of Oklahoma. And he is going to be talking to us about various activities in radar engineering.
Thank you, Greg. Okay, so good afternoon, everybody. We switch gears a little bit now and talk a little bit about engineering. It's really an honor for me to be here doing this review of the last 40 years and talk a little bit about the future. It's also a challenge because I've been with CIMMS a while, but not for 40 years. I was 7 years old when CIMMS was created. Of course, it took me a while to get here. But luckily, I've been able to experience firsthand most of the engineering accomplishments that were done in the field of radar in CIMMS. So what I did for the 20 years or so prior to my time was I went back to the written sources, the reports, the CIMMS annual reports, the NSSL reports, and I went back to the gurus, Dushan, Alan. They helped me put together some of this history prior to my time. So since we're switching gears, I thought I would remind people what engineers do. We're not chasing storms. We're not enamored of that tornado vortex. But what we do is, and I highlighted some of the keywords here from Wikipedia. Engineering is the creative application of science to the innovation, design, construction of systems, radar systems in our case, for the benefit of humankind. And when I saw that, I was like, this is the perfect example of that. What we do benefits humankind. In terms of weather radar engineering, I'm going to focus on 4 areas and under software infrastructure, signal processing techniques, and under hardware, a lot of work on radar systems and radar technologies. So I apologize in advance if I left out a particular project that doesn't fit this. I also have limited time, so I'm going to touch on just a few of the projects that sort of highlight CIMMS contributions over the last 40 years. Let's start with some numbers. I think it helps put things in perspective in terms of the timing and the scope of CIMMS contributions in terms of radar engineering. If we look back, we can see that the Doppler weather radar research and development theme was added in 1996. I went back through the CIMMS annual reports, and if you look at 1995, you don't see the Doppler weather radar theme, but you see it in the 1996 report. But there's some evidence of radar research and development before that time. So I think we were doing things before that time, and then the theme became an official theme of CIMMS. In 2011, the name was changed to just weather radar R&D. Obviously, we had done Doppler, we had done dual polarimetry, we were doing phased array radar, so it was time to just make it more generic. Now, if we look at the National Severe Storms Laboratory's radar division, we can see that 70% of the employees are CIMMS employees. And now if we dig deeper and look at just the engineers, 14 out of 18 engineers in RRDD are CIMMS employees. And if you look at, for example, the Advanced Radar Techniques team that I lead, all of us are CIMMS engineers. So that tells you how much of the accomplishments in radar engineering that come out of NSSL, for example, are also a result of the CIMMS partnership. So I went back in time, like I said, and I was trying to find what is the first contribution by CIMMS in the area of radar engineering. And Dushan pointed me to this report. Here's a CIMMS report, number 71. This is when we were numbering our reports sequentially. I don't know what number we would be at right now. And this is from July of 1986. M. Sachidananda here, or Sachi, was affiliated with CIMMS at that time. And what Dushan and Sachi did was they took Cimarron, which was actually the first research radar that could do dual polarimetry, and they implemented the computation of the polarimetric variables in real time for the first time. And here we can see, for the engineering geeks in the audience, the spectra of the H and V signals from that radar. So this is amazing if you think about the fact that this report was typed with a typewriter. So to have this type of data in real time was a really fantastic accomplishment. Since that time, from 86 to the mid-90s, I couldn't find a lot of evidence of contributions in radar engineering. Dushan pointed me to a couple of people, also researchers from India that came to CIMMS perhaps for a short period of time. There's Balki, there's Mahapatra. They all came for short periods of time, but things really stepped up, as Pam mentioned, after the deployment of the NextRed network. So we fast forward about 10 years, and we get to the mid-90s when CIMMS was heavily involved in the development of the WSR-AD-AD open systems. And here I'm giving you 3 keywords that are confusing everybody. So I thought I would use an analogy to describe what open systems is supposed to do. So let's say we have an old recipe box, and in this analogy, the box would be the hardware and the recipes would be the software. So let's say, you got this recipe box from your grandma. The recipes are a little bit outdated, but you want to keep some of them. You want to get new ones. So you go to the store. You get recipe cards, and they're vertically oriented. So they don't fit the box. So this goes to the issue of interoperability. If you do not have the ability to use recipe cards from another vendor or another source, you cannot insert new recipes into your box. Let's say, on the other hand, that you're tired of the box, the painting is chipping and the lid doesn't stay open, so you go to the store and try to get a new box, but the box is a different size. So there's no way you can transfer your old recipes to the new recipe box without, for example, having to retype all of them. So that goes to the issue of portability. So if we cannot use 2 different boxes with the same recipes, that is, 2 different computers, for example, running the same type of code, then we have a problem, and this is very, very frustrating, as the young Eddie Foreng is showing here in this picture. So now going back to reality, in the mid-90s, we have, in 1997, is when the last WSR-AD-AD radar is installed as part of the NextRed network. Now we rewind a few years back, and even before the National Weather Service was done with that installation, they realized that in order to support evolution of the system, to keep up with new technological upgrades, they had to do something about it. So they embarked into the Open System project that aimed to replace all the computing infrastructure with open systems that allow you that interoperability, that portability, that were based on open standards. I know we can argue whether they really accomplished that or not, but that's a separate discussion for when we go to the poster session if you are interested. But I'm going to highlight that CIMMS contributed significantly to the Open RDA. So we retrofitted the KOUN radar, our research radar, and upgraded all its computing capability to be based on open systems. I was part of that project. It was actually the first dual-pole WSR-AD-AD radar, and it was the proof of concept for a future upgrade of the network. There was also the OpenRPG project that aimed at replacing the second block, the radar product generator, actually the RPG is in use today. And it's the system that runs all the algorithms, like tornado detection algorithms, quantitative precipitation estimation, and it also serves as the user interface with forecasters and allows forecasters to control the radar, to operate the radar. And finally, there's OPUP. OPUP was a little bit of an obscure project that only the DoD funded, but OPUP is basically a system that captures all those products and archives them and makes them available to the Air Force. And so that was also another big project that where CIMMS had a big part. So now, going to the signal processing techniques, I also wanted to introduce what signal processing means. A lot of people in the audience may not be familiar with this term. So basically, if you look at the radars received by the signals received by a radar, they would look something like this diagram on the left. Basically, it's a lot of data, incomprehensible. What signal processing tries to do is to convert that data into usable information, usable to the forecasters and algorithms, models, things like that. And Jeff Kimple, when we were doing the lab review, one time said, radar signals are messy. You have to emphasize that. So here's the message again. Radar signals are very messy because in addition to the rain, in the same area the radar is looking at, you may have other things like trees, terrain, planes, towers, and all of these things need to be removed. The data needs to be cleaned up, as Pam mentioned before, and not only for the forecasters, but also for the models, for the algorithms. So here comes our geeky signal processing superhero to take all of that away and clean up your radar signal. I'm going to show you some examples of that. For example, getting better velocity data. Here's a Doppler velocity field. The red colors indicate the wind is moving away from the radar. The green colors indicate the wind is moving toward the radar. And you can see some situations where greens and reds are next to each other. And you can tell that nature is not doing that. This is a problem with how the radar is processing the data, but if we use one of our super techniques called stagger PRT, we can clean that up very nicely. Here I'm going to go back and forth again. A stagger PRT is actually a technique that was developed here and actually in a way that could be implemented operationally on the next network and actually has been transferred to operations. It's not operational yet, but it's in the process of becoming operational. Another example is contamination from echoes from the ground. You can see here in these panels of reflectivity, velocity, differential reflectivity, and correlation coefficient, how you can see some elevated echoes close to the radar, and also you can see some footprint corresponding to terrain. It's very dramatic in correlation coefficient. You see it, it stands out very clearly. Now, if we apply our super techniques, wet and clean AP, you can see how that contamination goes away. And this will be very useful if you're doing, for example, precipitation estimates, because you're not going to count rain where it's not raining, for example. We developed wet and clean AP solely within CIMMS. Actually, we have licensed clean AP to a private company, and we actually transferred clean AP to the UK radar network of weather radar. So we have transferred it to our National Weather Service, to a foreign National Weather Service, and to a private company. This is also an example of how CIMMS connects to government, nationally, internationally, and also with private companies. In terms of research to operations, here's a number of techniques that we have either transitioned into operations, that we are currently in the process of transitioning them, and some that are just in the research stages. R2O is a very key mission that CIMMS fulfills in helping the NOAA mission. And you can see, for example, here systematic phase coding was operational in 2007, but the first report that shows some research in this area is from 1997. So 20 years of research before this technique could be implemented operational. So the other techniques, again, CBT, also developed by CIMMS researchers, radar noise estimator also. So a lot of contributions in the area of signal processing. So we have a number of geeky superheroes in the audience. Radar systems, also big in terms of CIMMS contributions. We have KOUN in the mid-90s. Again, like I said before, the first WSR ADAD radar that was dual polarimetric radar. Pam talked about the National Weather Radar Testbed, the first phased array radar that was used for weather observations with a lot of important results. As Pam mentioned, we have also strong involvement in the development of NOXP, a mobile X-band dual pole radar that participated in a number of campaigns. And more recently, the 10-panel demonstrator, we did not develop the system, but we did a lot of engineering research with this system to understand how one could calibrate a phased array dual polarimetric radar. So a lot of research and development in terms of systems here. I'm going to talk a little bit about our phased array radar because it's, it's part of our history, but also a huge part of our future. As Penn mentioned, from 2003 through 2016, we have what I call the legacy NWRT PAR, and that supported a lot of interesting demonstrations. Penn talked about the rapid updates. Here I'm showing again an animation that Penn provided with PAR versus conventional radar. We also were able to demonstrate that you can scan not in the usual way, but you can adapt to the storms that are out there. And you can have faster update with some storms and slower updates with other storms. And we could also show that a single system could be used with two functions. The weather surveillance function and the aircraft surveillance function were combined, and here you can see displays of reflectivity data with aircraft tracks intermingled. So a lot of important things were done with this system. But if you were to look inside the radome back then, you would have seen a system that was based on outdated technology, that was a passive array, and also used single polarization. So what NOAA decided to do in collaboration with the FAA was to trash that antenna, even though we loved it, and replace it with one that uses modern technology. It's an active array, and it's dual polarized. So CIMMS has been very involved in this process. It's a $38 million investment from the FAA and NOAA, and we collaborate with other government, industry, and other universities. So very, very important. In terms of designing the radar of the future, when we cannot build a radar, we have to simulate it. So there's a lot of expertise within CIMMS in terms of simulating radar systems. And I'm running out of time, so I'm going to accelerate a bit. And so to look at the future or to foresee the future, it's important to look at their past. And we can see through our past that we have been part of all these revolutions in weather radar observations, from the addition of a network that produced reflectivity data to the incorporation of Doppler velocity to the dual pole. And so what's next? Obviously something related to phased array radar. Is it MPAR? Is it NextPAR? Is it MPAR? All these acronyms are being thrown out right now. Something that would be beneficial for the forecasters and also for the prediction for the models as well. So my prediction for the next 40 years is that we're going to be investing a lot of time and effort on making operational use of phased array radars. Right now it's being used for research. We want to address the technology obsolescence of the current system, and we also want to, of course, improve weather surveillance. We want to fill observing gaps, retrieve data, other kinds of data from the radar data, and also we want to go perhaps into hybrid observing system networks to improve the quality, the coverage, and the availability of radar data. To end, I'm going to say that the partnership between OU and NOAA is the perfect partnership to save lives and property. Thank you.
Okay, we have time for questions. Okay, yes, Marion.
You want to comment about in the next 40 years with regards to all digital phased array radars?
Yes. So all digital architecture is an architecture that, let me backtrack a little bit for the people who are not fully familiar. A phased array antenna is composed of thousands of smaller antennas. So if you have an all digital architecture, that means that you have thousands of radars actually that are digitizing the signals, and then once you have digital signals, you can do a lot of things. The problem right now with that is that first, it hasn't been proven. It's being proven by our community, but it hasn't completely been proven. And so but on the other hand, the capabilities that kind of architecture would provide are really, really important to the National Weather Service mission. So in terms of providing calibrated, good quality, dual polarization data, it's very important. So I see, for our future, I see us looking into, of course, that as an option, and as we move forward, obviously technology costs are going to decrease, things are going to be, things that right now seem to be impossible are going to be feasible. All we had to do is look 10 years back and look at the technology back then, and so it's very easy to see that in 10, 20 years, things like an all-digital phased array radar would be possible.
Okay. Any others? Well, let me ask, do you think, we've talked about phased array radar in the next 40 years, do you think there's any other new, unique observing capabilities that might be complementary with the use of phased array radar in the next 40 years?
Well, when we talk about radar coverage, it always, the idea that we're not really observing what's happening close to the ground, especially when things are far away from the radar, that makes us think that we need to fill those gaps. So there might be, ways to fill those gaps, maybe not using phased array radar technology, but using conventional technology. We can also go into other ways of getting useful data, for example, using communication links. That's one of the ideas that is being proposed currently as something for the future. Also the idea of having radars on balloons, stratospheric balloons looking down and kind of complementing observations from the ground. So I think, there's a lot of things out there that in the next 40 years, who knows? Right now they appear to be esoteric, but, it's a matter of time.
40 years is a long time. So anyways, let's thank Sebastian again. Our next talk is going to be given by Adam Clark. Adam got his bachelor's, master's, and PhD, all from Iowa State University. His dissertation was predictability associated with convection allowing and convection parameterizing forecasts. He worked as a research scientist at CIMMS from 2011 to 2015. He's now a research meteorologist in the National Severe Storms Laboratory, and some of his tasks, he's a planner and facilitator of the annual NOAA Hazardous Weather Testbed Spring Forecasting Experiment, and he's also lead scientist on the development, maintenance, post-processing, and verification of experimental real-time high-resolution ensemble prediction systems. So he's going to be talking about the storm scale modeling at CIMMS, 40 years of cutting-edge science.
All right, thanks, Greg. Wow, that was a mouthful. So here's my cover slide, but Jeff, I'm glad you didn't include that picture at the top left up there. That is Doug Lilly and then Ed Lorenz, who made a visit. I would guess this is back from the late 80s when this was taken, and this was outside of the old CIMMS building that would have been in one of those locations that you mentioned. I'm not sure which one. Okay, cool. So these were really two giants in the field of numerical weather prediction. Ed Lorenz came up with what is known as chaos theory, and Doug Lilly was also a big contributor to NWP. He examined rotation in supercells and the implications on storm predictability and dynamics. So that was kind of neat to find a picture of those two kind of famous scientists together. I also liked what you said about the logos, because right before I gave my talk to Emily, somebody pointed out that I had the illegal logo. And so I changed that quickly to the legal one. So I'm safe from the NOAA lawyers now. So I hope I'm safe. We'll see if we can get through the talk. So I wanted to have a little disclaimer to start off. Sebastian, you mentioned that you were 7 years old, I think, when CIMMS started. I got you beat. I was -1 years old when CIMMS was founded in 1978. So that means I needed a little help putting together this talk, and these are the folks that helped me. I went to each of the people here, Lou, Harold, Eric, Jack Kane, Dave Stenzard, and Jeff all gave me some really useful information. And of course, there's a reason that they were able to provide this information, and I decided to represent it mathematically. I usually don't include equations in the talks that I give, but here that I think adequately explains why they were able to provide this information. I'm not trying to rub it in or anything, it's just a fact. I just realized there should be an over bar in the first image there anyway. That's okay though. That's why I don't put equations. Okay, so I decided I'd go about this very systematically. I figured 40 years, and I can divide that into 4 decades and talk about each decade. So in the first decade, really the main research from what I found that was going on at CIMMS was observational studies of storms and weather radar development. There really wasn't any storm scale modeling going on yet. But I did find this picture of Lance Rothfuss, who I learned was a CIMMS employee back in 1987. And he did work with this tornado vortex simulator, which I thought was pretty neat, and I wanted to embarrass him by putting this photo up there, so I figured I'd use that opportunity. And during this decade, really the foundation for storm scale modeling was being developed outside of CIMMS. So Joe Klemp at NCAR and Bob Wilhelmsen at the University of Illinois were really 2 of the main figures that got this started. So this paper, Klemp and Wilhelmsen, 1978, really laid out some of the basic equations for modeling 3-dimensional convection. And then you've got Wiseman and Klemp, Rotuno et al., 1988, the infamous, you could call it infamous, but the very well-known RKW theory for long-lived squall lines was outlined in that paper. And so that's just some of the pictures of the folks that really got NWP for storm scales started in the 1980s. Okay, so the next decade, decade 1 was easy because there wasn't much going on. In decade 2, though, a very important event happened, and that was Doug Lilly becoming the director of CIMMS in 1986, and then him and Kelvin Drogemeyer writing the NSF proposal that basically established CAPS as an NSF technology center at the University of Oklahoma. And they made this kind of argument for CAPS, and they set out this vision for the future of storm scale modeling. And Doug Lilly has this paper in 1990 called Numerical Prediction of Thunderstorms Has Its Time Come. And this was a really interesting paper to read because some of the things that Doug predicted in it are exactly what is happening right now. And some of the issues and really some of the things in this, I mean, he was very forward thinking, so it was just fun to read. And I just have some quotes up here from this paper. And Doug says, weather prediction is the principal reason for the support which we are given by our fellow citizens. I am personally impressed with the quality and dedication of the scientific efforts now being made in operational weather prediction. I believe it is time for convective storm scientists to apply our knowledge to this purpose and to subject our products to its discipline. So this was kind of an important statement because up until that time, storm scale modeling was being done to understand storms, their structure, their dynamics, but it was never really envisioned that they would be used for operational prediction of storms. And so Doug put that vision out there, and that kind of started, I think, the idea of storm scale modeling for an actual prediction tool. And he also said that the key observing system is a Doppler radar network. That's very true, and that there is great scope for scientific, technical, and artistic creativity in developing imagery suitable for rapid dissemination and short-term predictions. So that, I thought, was a great thing to say. Right now, one of the main things that CIMMS scientists do is come up with creative diagnostic and visualization tools and verification methods that forecasters can use for storm scale models and predictions. Okay, so now in decade 2, we're still in decade 2, there still wasn't much actual storm scale modeling going on. I put storm type up here. This was an experiment that was led by Harold Brooks and Lou Wicker. They kind of count as CIMMS because each of them were CIMMS, I think, for less than a year before they became federal employees at NSSL. And this was kind of a cool collaboration that they did with the National Weather Service, where they used this very crude, I guess the model itself isn't crude, but it's homogeneous, so you just give it an environmental sounding and then integrate the model forward. So there's no, you're not depicting any topography or boundaries or anything like that. And then you initiate storms with a warm bubble, and then you just see what kind of storm type that you get from the model, and then you can use that for your prediction. And it turns out that it actually worked pretty good. And Harold told me this story about how they actually used one of the forecasts for a storm chase. And I would guess that this would be the first ever instance of a kind of a successful storm chase based on the prediction from a storm scale model, all the way back in 1991. So, Harold, I don't know where you are, but that's pretty good. Oh, there you are. Okay, good accomplishment. Thanks for the story. So in the late 90s, I think a key event was SPC moving to Norman, Oklahoma. And in preparation for this move, NSSL created this small group of scientists called the Mesoscale Applications Group. And this was NSSL and CIMMS staff that would collaborate with SPC when they moved down here. And they created this thing, this area in the old building called the Science Support Area. And this is just a picture of what that area looked like. I think you'll see some familiar faces there. I think I see Don Burgess, I see Jack Kane, Harold, you're in there. And then I think that's Bob Johns on the left side. So, okay, so something really important happened in 2000, and that was when the spring program really became formalized. And that's now known as the Spring Forecasting Experiment. And so really the pioneers of the SFE were Jack Kane, Mike Baldwin, who were both former CIMMS employees, Paul Janish at SPC, Steve Weiss, and Russ Schneider. And so this, well, at least what the SFE is now, it's a 5-week-long forecasting experiment to test emerging concepts and new technologies for improving severe weather prediction. And those tools are accelerated into operations. And so a big part of that has been the use and application of storm scale models. And currently, it's used as kind of an experimental testing ground for documenting the sensitivities and the performance characteristics of storm scale models. And so these are just some action shots from the experiment. What's great about the HWT that we have now is that we basically are able to replicate an operational forecasting environment. So it's this kind of sense of realism that you have when you're participating in these experiments. You have to abide by the same types of time constraints that forecasters do. You're using the same types of tools that the forecasters use. So it's just kind of a really fun, enlightening experience. And it brings together a very diverse set of backgrounds. So forecasters, researchers, academics, and you learn a lot that way. And there's a lot of back and forth and people learning from each other. So decade 3, we are now into decade 3. This was really when research on storm scale models for prediction really kind of took off. And really, in the hazardous weather test bed, we started looking at these models in 2003 and 2004. And Jack has a paper where he kind of summarized what was done. It's Canadell 2006. And so the thing that forecasters realized that was so valuable about these models is that you got this explicit prediction of storm mode, which was not something that you got from the older generation of models. So this meant, you look at the simulated and the observed reflectivity, that in a situation like this, where you have a squall line, and then ahead of the squall line, there are isolated cells that were tornadic, that you could actually, predict this. The model would depict it. It wouldn't get the locations exactly right, but it would accurately forecast the mode most of the time, which is huge for forecasters. And John Hart, one of the lead forecasters at SPC, when he first looked at this data, commented on its usefulness and said he could use it to delineate where watches would be required. And forecasters also called it a turning point in the use of model output. So this was great. And then another thing that happened was that Jack Kane established the NISSLWRF, which is managed by Scott Dembeck of CIMMS. And so this is kind of a permanent modeling framework that was used, and this started in 2006, so this is a full 5 years before a convection allowing model was operational at the Weather Service. So it allowed the Storm Prediction Center to be able to use this tool that they wouldn't have operationally for 5 years. And so when it became operational, they were experts in the use of CAMs, or convection allowing models. So this was really important. It was kind of this testing ground for new diagnostics in these models. So many of the diagnostics that are used today, like updraft helicity, originated from the NISSLWRF. And we have an archive that goes back to 2007, which is by far the longest archive of a data set like this. And it's been incredibly productive having this around. And I think, nearly 100 publications have actually used the NISSLWRF data. So that's just it's a really big deal. And it's also, this configuration of the WRF model is also run operationally and as part of the operational convection allowing ensemble for the Weather Service. So these are some of the people that contributed to the spring forecasting experiments that were CIMMS back in the previous decade. So it looks like it's a fairly large group, but wait till you see how many people contribute now. In 2007, the experiments began to focus on storm scale ensembles. And this is a full 10 years before storm scale ensembles became operational at the Weather Service. So again, we were very forward thinking in what we were doing in the HWT, and this allowed us to develop all of these tools for these types of systems before they became operational. Okay, so, I'm gonna have to accelerate big time. But some of the diagnostics that were developed were very important. Verification techniques were honed because of the work that was done in the test bed, and also CAM visualization tools. And the first website for viewing the first operational CAM ensemble was created by a CIMMS employee, Brett Roberts. This was just last year. So this was a really big deal and is a very important tool for the Weather Service for forecasting severe weather. And also the Community Leverage Unified Ensemble is an initiative that was started just a few years ago and is contributed to by several CIMMS people. And so this is important for kind of optimizing operational CAM ensemble systems at the Weather Service, and is contributed by several external agencies. Okay, so these are the people from the current decade that support the testbed work. So like I said, a lot more people. Also, one thing that I noticed when I put this together is that the previous group was all males, and so now we have quite a few more female scientists that are contributing to what we're doing in the testbed. So that is definitely a good thing. Warn on forecast. So this has been huge at CIMMS. And really the concept of warn on forecast is that we can use the same idea that the Hurricane Center uses, where you have this cone that's based on model guidance, and we can do this for thunderstorms. So really the motivation for this is to address the gap in guidance between the watch and warning timescales. And I just got red carded by Emily over here, so which I kind of like. I like soccer. I'm a soccer referee, so I'm kind of into that. This is basically my goal, was to get red carded in this talk. So, So this is what Warn on Forecast looks like today. These predictions, they go from 6 hours down to 3 hours where we're really getting these narrow corridors storms. And then by the time we get to 1.5 to 1 hour predictions, really we're giving information on the warning time scale. And this was an instance of a very accurate forecast from just this past year of a tornado that occurred in Kansas. So how did we get here? We did a bunch of stuff, like all kinds of research. I can't even tell you how much. It was a big amount. So proof of concept, resolution, sensitivity, and predictability. Corey Potvin has been a big part of this research. He was a PCASE winner. I warned him that I was going to tell a joke about him, and so here it is. Are you ready, Corey? Corey has a dark side. This is a picture of him from the most recent SLS, and it may look rather like nothing's going on here, but he's taking some ice cream, but he trampled several children to get to the ice cream. So Corey, yeah, you better stop doing that. Okay, so Greg's getting up. Basically, I'm just outlining all the stuff that has made Warn on Forecast great, and these are the people that have contributed to it, a big group of scientists, many students, and here's the future. Okay, so CIMMS scientists are going to continue to have a really big influence in storm scale modeling, and especially on how future configurations of operational models will be developed. Warn on Forecast will go operational. That's going to be huge, and it will probably change the way that research is done for Warn on Forecast when there's an operational system, and then at the same time development and research going on. And I'll just leave it at that and take any questions.
Okay, do we have time for one or two questions? Okay, do you think anything, we've talked a lot about Warn on Forecast as one of the new techniques. Now thinking about what's going to be the new technique in 20, 30 years, do you see, what will the future hold beyond that?
Yeah, it's hard to even imagine what we'll be doing in 20 to 30 years. I mean, if you look back 20 to 30 years ago from today, how crude the modeling systems were. But, as we get faster computers, we'll be able to use much higher resolution. I hope in 20 to 30 years we'll be resolving tornadoes and we'll be making extremely accurate predictions of them, 1 to 2 hours in the future. And really the big hurdle that will have to be overcome will be data storage. And I don't know how we're going to address that, but that's going to be a big issue. But I'm sure we'll figure it out. There's lots of smart people that are really young, and they'll solve all of our world's problems. So.
And would you say the bigger limitation is computer resources or physical understanding at this stage for making the next development?
Well, in my opinion, it's computer resources. So, I mean, we still have a lot of gaps in our understanding, but yeah, to me, it's computer resources. You can disagree if you want, but.
We'll save that discussion for later. So anyways, thanks again for your nice talk. And I'd like to move on now to our next talk, which will be given by Don Burgess. He is currently a research fellow at CIMMS, but he's had another career too. He is retired as chief of the Warning Research and Development Division at NSSL. He has also served as acting director and chief of operations at the NEXRAD Radar Operations Center and chief of the National Weather Service Radar Training. He received his master's from the University of Oklahoma. He's also a fellow of the American Meteorological Society. He has over 50 publications and over 200 conference papers, and he has also served as an adjunct professor of meteorology at the OU School of Meteorology. So let's welcome Don for his presentation on forecast and warning improvements.
Thank you, Greg. Well, I wanted to start by mentioning, as others have, that I'm going to be talking about partnerships between CIMMS and NSSL and the Rock in a lot of what I'm saying here. And these partnerships are so strong that the work is integrated. And so I'm not going to separate things out. CIMMS is a strong partner in all the things that I'm going to be talking about. Also, I'm going to be slightly different than some of my colleagues. They have mentioned some of the individual participants. And I wish that I could do that, but I just don't think I'm able because there are so many important participants that I've just kept this more general. If you're out there and you've done some of the work, I hope you can take comfort in seeing some of your results presented up here. Back when CIMMS was young, 1980-ish, we were still learning about some of the basics. We were learning about experimental Doppler radar signatures. We were learning about how they tied to storm structures. We had very little understanding of radar meteorology out in the field among forecasters. We had some projects like Project Doplight that took Doppler radar and lightning to Weather Service offices. CIMMS people participated in that. We also had Scientific Storm Intercept that went out to verify the radar signatures and the understanding of the storm structures. And CIMMS participants there made contributions. We also were trying to get a better understanding of mesoscale meteorology and near-storm environments for these kinds of storms. I know the next talk will talk about some field programs, but I stuck something in from Project Sesame in 1979 with a surface mesoscale map near the time of the tornado outbreak on April 10th of 1979, Wichita Falls tornado. Going forward, we started thinking about the initial deployment of the WSRAD-AD, the NextRad program, and thinking about detection of severe storms and displays and algorithms. And so some of the focus of the work in this partnership became the first type of displays and algorithms that went into NextRad. And you can see at the bottom, I have listed some of the algorithms that were initial algorithms that came from the work here, the SCID algorithm, hail algorithm, the velocity wind profile, VAD, mesocyclone algorithm, tornadic vortex signature algorithm, and a de-aliasing algorithm. So all these things contributed to the initial NextRad deployment. I can show you some examples here in the upper left for an outbreak in 26th of April, 1991, the Andover, Kansas, Red Rock, Oklahoma tornadoes. This outbreak occurred while the Twin Lakes radar was experimental, had not been accepted by the government, and it was some of these days like this that allowed that acceptance to occur and deployment to begin. So here you see the reflectivity field, and you see the storm tracking or SCIT output. It seems kind of elementary to us, but it was somewhat revolutionary in those days. This is velocity depiction with a mesocyclone signature and some information about that. And then on the right is the VWP, the wind profile. This was in clear air in central Oklahoma, and you can see the development of the vertical wind shear that was contributing to this tornado outbreak. So very good initial work, CIMMS and partners contributing to the first deployment of the WSRAD-AD. But also improvements to the WSRAD-AD over time. I'm going to be talking here about single radar algorithms, and there's a whole litany of them. You can see mesocyclone detection algorithm. It goes on down tornado detection, hail detection, near storm environment, gust front, microbursts, improved velocity de-aliasing, multi-PRF de-aliasing algorithm, and rapid update of algorithms all came from this partnership that I'm talking about. And there were some algorithms that didn't get deployed in the 88D for various reasons. the damaging downburst and prediction algorithm, and also the bounded weak echo region algorithm are in that category. Then we have dual polarization algorithms, the hail size detection algorithm of which some of you are aware. This is an example in the upper right. You can see the large and giant hail categories that come from dual pole information. Also, we have the tornado debris signature algorithm from dual pole information. That's still experimental, but we hope it will be made operational in the future. An example of it's on the right. Here you can see a tornado debris signature example. It is shaded, which is confidence. Is that shading? The bright white is the highest confidence, and as it degrades down to blue, that's lesser confidence. Then finally, at the bottom, some experimental algorithms that are being developed right now, a new mesocyclone detection algorithm, a new tornado detection algorithm, and a new hail detection algorithm. And there are some posters that will be presented later this afternoon on those experimental algorithms, and I think it would be a benefit for you to check with those folks about further information. In addition to just algorithms, a lot of work was done with displaying the data. Forecasters want to look at the data, they want to see the signatures for themselves. They do rely on algorithms, but more as the second line of defense. The first line of defense is looking at the data. And when we began back with the early deployment, we had displays that didn't display the full resolution of the WSR88D data. The so-called level 2 data or full resolution was not available, and that only came as a function of time. The first displays done by NSSL, a system called WAD-ADS, and those were put at Weather Service forecast offices to start seeing that data and seeing how it might benefit them. Also had algorithm data. Became the warning decision support system. There's an example here in the lower left at the time of the May 3rd tornado outbreak in Oklahoma, and you can see here the track of the mesocyclone from the Moore supercell as it's headed toward the town of Moore. Then those have increased over the years. SCAN, the System for Convective Analysis and Nowcasting, and then in AWIPS, the Four-Dimensional Storm Scale Investigator, or FSI, and here is an example of that display. Many ways to slice and dice the data at its highest resolution to get the most information out of it. Also, you may not be aware that when NextRad came along and the 88D radars were deployed, they did not have a good concept for archiving this base data, the level 2 data. And it was through the work of CIMMS, NOU, and partners and NCDC that we actually have the archive system that we have today, starting with an experiment called CRAFT, Collaborative Data Acquisition Field Test. We began to use the growing backbones of the internet to start moving some of the data into Norman first, and then later to NCDC. And we even had, for several years, a center here in Norman with CIMMS as a participant called the Integrated Radar Data Services Program. And you can see here in the lower right, in 2001, in Norman, we were receiving and archiving the data from 57 radars. So this internet archiving system didn't come immediately, it came in pieces. And we had an archive here in Norman from 2001 to 2004, at which time we then transferred it to NCDC, or now NCEI. Those improvements that I've talked about contributed to National Weather Service skill scores for warnings becoming better. I would call your attention here to a diagram of probability of detection on the left, on the vertical axis, and year on the horizontal axis, and the thick red line. And you can see that the probability of detection was not very good before NextRad implementation. It improved by about 40 points during the time of that implementation, and we went from about 30% probability of detection to about 70% probability of detection. So a significant improvement, and that led to a Department of Commerce gold medal that Pam has already mentioned. And CIMMS was certainly a participant in that medal. Now I want to transition, see how I'm doing here on time, still alive. Transition to going from single radar to multiple radar. Those systems that are multiple radar and multiple sensor in their applications have a significant advantage over any single radar system for very obvious reasons. And so that research has been going on at CIMMS and partners for quite a long time now. System was first called QPE CIMMS, but then before too long was changed to MRMS for multi-radar or multi-sensor. And for severe storms applications, which is kind of my theme at the moment here in this talk, the applications are rotation tracks or shear swaths, and then the maximum expected size of hail or mesh in its swaths. And at one time, NSSL had an experimental on-demand system for sending out this information to interested users, and that very much involved CIMMS. Here in the lower left is an example of rotation tracks. This is for the rather historic tornado outbreak that occurred on April 27th of 2011. Many supercells down here in the southeast, and you can see the individual tracks of those supercells, and even as it extended over into the mid-Atlantic states. These data are very useful for deploying resources for rapid search and recovery and getting aid to victims, and they're also useful for damage surveys, knowing where to look for the tracks of tornadoes. Here on the right side is an example of mesh, maximum expected size of hail, and you can see in colors here the depiction of large and giant hail. I think this is up in South Dakota, storm moving from northwest to southeast, but you can see the long extent of the track. You can also see overlaid reports of hail that came from a special program that was done here in Norman, CIMMS and Partners, Severe Hazards Analysis and Verification Experiment, or SHAVE. And it was a very important contributor to getting the data to say what is a good algorithm to identify hail, because if you look at National Weather Service reports, which are marked on here, there are so few reports that you can't do verification with that data. Now I want to switch for a bit and talk about advances in quantitative precipitation estimation, QPE. And I want to thank Jen Zhang for sharing with me her slide that kind of has a nice depiction of all that and a timeline, and talking about single radar applications at the top for QPE, and then multi-radar or multi-sensor applications at the bottom. And with single radar, we had an initial system in the WSR-88D, which was reflectivity-based, PPS. And then in later years, we've had single Doppler systems that have involved dual pole data. And there's been an improvement because of that. But you can see here with the long development, including craft and being able to get the level 2 data, how we've been developing multi-radar, multi-sensor systems. And in 2014, then we had a full multi-radar, multi-sensor, and dual pole system for estimating precipitation. Whoopsie daisy. So I got ahead of myself. I was right here. And then we're just on the verge of even a newer and it looks like better system using attenuation with dual pole information, and the skill scores here are even better than the preceding systems. And I have been failing to mention, but for a number of these slides there have been posters that are going to be presented this afternoon. So please excuse the fact I haven't mentioned all of them, but hopefully you've looked at them as we've gone along. Also, this work then led to a Department of Commerce silver medal in 2015 with CIMMS as a partner. Was that the yellow one or the red one? All right. I only have a couple more. I don't think I'm getting my full 20 minutes if that was the red one, but I'll go with that. Because I'm keeping track of time myself. With these MRMS QPE systems, we've done some really interesting, innovative things. We have a flash application. I don't have time to tell you a lot about it, but you can see when there's a threat here in North Texas, we can compare the rainfall estimate to the flash flood guidance. We can also look at the estimated stream flow, and that allows for better flash flood warnings. And we can also look at river systems. We can even look at storm surges with hurricanes as an example in the Coastal and Inland Flooding Observation and Warning Program, CI flow. So there are a lot of these applications in QPE where we're doing very innovative things and now being transferred to the National Weather Service. One thing I do want to explain, even if I'm about out of time, is that these forecast and warning improvements will not occur without training. We can develop all kinds of good things, but if we don't train the forecasters in the use of that information, then they're not going to succeed. So we have a long history of that collaboration with CIMMS, and that's both in the severe storms area and in the QPE flash flood area. And a number of names of this organization, Operational Training Branch and FIRST and Warning Decision Training Branch and now Warning Decision Training Division. And they've done things like tornado warning guidance that was very helpful to the field, distance learning courses, workshops, and weather event simulator. CIMMS people making big contributions, some of them standing up here heading workshops, first at a separate building in the past and now here in the National Weather Center building. This is a front of the weather event simulator. It is a very important device because it allows delayed real-time playback of data and allows forecasters to go ahead and practice their skill and be scored on important events. And all the data necessary, radar and other sensors, has been captured in the WES. Ask about forecasts and warnings of the future. The program here is FACETS, forecasting a continuum of environmental threats. You can see it has a radar grid-based and probabilistic background. It contains a number of other elements that I'm not going to go into, and it has the forecaster funnel concept from days and large time increments down to just minutes in very small areas. And I will stop with what the future might look like if we're using FACETS and we have an April 27th tornado outbreak. You can see in the dark blue is the smaller amounts of threat, and as we go to the brighter colors all the way to the white, which is extreme threat. So this is how a FACETS system might handle a tornado outbreak in the future. And with that, I'll stop and say thank you.
Okay, thank you very much. We'll have time for one or two questions, so you don't leave yet. Does anybody have a question or two? Okay, we'll ask one very quick question then. So you've talked a lot about our activities such as FACETS, MRMS, and of course the conventional radar. Do you see anything really new that will revolutionize what we do? Like, 40 years ago, I'm sure you couldn't foresee MRMS or FACETS or anything. Do you have any idea what might be new coming on?
Well, I didn't mention it. But with FACETS, we have a continuum of threats. And what I see is the merging of programs like Warn on Forecast and these experimental kind of products that I've been talking about and what the radar can sense and how we can put that together, put that with Storm Prediction Center information, with storm scale models, and how we then would have a continuous flow of information and be able to handle the threat as it evolves.
Okay, well, thank you very much. We should keep moving along then. So yes, thanks to Don. Our next presentation will be given by Eric Rasmussen, And Eric, he received his bachelor's degree from the University of Oklahoma, his master's from Texas Tech, and his PhD from Colorado State University. He right now works as CIMMS as a senior research scientist and also as the Vortex project manager. He also won the Presidential Early Career Award for Scientist and Engineer. And really what he has got most of his reputation in the community is for a lot of field campaigns that he's been involved with. He was the field coordinator of the first of the Vortex projects in the 90s, lead principal investigator for Vortex 2, and now he's heavily involved with Vortex Southeast. So he is the ideal person to tell us about CIMMS' role in field projects.
Thanks, Greg. Let's see. So I was a little surprised at that introduction because I gave material to Greg very late, and there was sort of a threat made that he would bring up the fact that I was called the dry line kid in some earlier popular literature. Thanks, Harold. But he refrained, so thanks again. So this is going to be another talk where I'm not going to be able to acknowledge everyone who's been at CIMMS and been involved in field work because there are so many, and for our earlier work, it really wasn't very well documented who was out there, that we had a lot of undergrads and graduate students in the field. Something that doesn't get mentioned a lot is that we've had people at CIMMS who have been very instrumental in developing instruments, such as mobile Doppler radars, mobile mesonettes, and that sort of thing, and their efforts don't get acknowledged as much as they should. People in CIMMS who do the grant administration and take care of travel orders that change daily for 12 or 24 participants. And then we have people in CIMMS that have been involved in science leadership in these field programs. So I'm going to give you a quick chronology of where we've been in the last 40 years. Yes, I was cool. And yes, I was a kid when there still was a dry line. Back when CIMMS started, this is how field work was done in terms of making storm observations. You would go to the Weather Service office, stand by the teletype machine, and as observations came in every hour, you'd plot them on a map, figure out where you ought to be chasing storms, and head there. There was no internet when CIMMS began. Then if you needed observations, you ran a dryer hose in the side of your car window to a hygrothermograph sitting in the back seat. And then you took those strip charts and figured out where you were for every event on the strip charts, and you plotted them on maps and figured out where the rear flank downdraft was and the gust sprints and all of these things. So it was a different time in 1978. In those 15 years that followed the beginning of CIMMS, a lot of the field work involved development of specific instruments to do specific tasks. There wasn't really any coordinated field observing. It was more like, let's go and see if we can find out what's going on in tornadoes in terms of wind and pressure. So we go and take this instrument in the top center called Toto, and we take it to the field and we yell, deploy, 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 and roll it off the back of a truck and make some observations. Mobile ballooning was just starting during that time period. There had been, of course, radiosondes could be done from fixed sites, but from mobile sites, it just wasn't done. So that was invented and pioneered here in Norman. Oh, I wanted to make one comment. That guy in the lower left picture with the phone in his hand, I just wanted to point out that Don Burgess hasn't changed at all in 40 years except for the length of sideburns. There were some larger multi-agency campaigns during that first 15 years. One was pre-storm, which was, again, a fixed network of instruments, surfacites, and balloons, looking at the mesoscale influences on storms. There was not much of a mobile component that I can recall in that experiment at all. GUFMEX happened in 1988 to find out how the air gets modified over the Gulf of Mexico and how that influences the thunderstorm evolution onshore. This one actually had a mobile component called aircraft, a C-130 and a P-3. And they had soundings out there on oil platforms, which is something I wish we could try again, because even in the last few years of Vortex Southeast, we're having a lot of trouble understanding that return flow of moisture off the Gulf. COPS 91, this is during early 90s, there were actually fixed site profilers that were operational in the Weather Service, and some of these were in the central U.S., and their data was really very helpful in understanding the environmental evolution leading to storms. So something really big changed in the mid-1990s. Vortex 94 and 95 was our first attempt to do truly mobile observing. And the plan on the left is our design of where we would put instruments, cameras, balloons, the little anemometers, a mobile mesonet. There's a little turtle in there, which is a deployable a turtle, a little triangular or pyramidal-shaped device with pressure and temperature sensors that you put on the ground. It's sort of like the device Tim Samaras pioneered a lot further. But then another thing is on the right is we had mobile field coordination, so we could actually track where every team was and make sure they were in the right spot to do their missions. It wasn't quite as sophisticated as you might guess from that image, because what would happen is the FC, the field coordinator, would yell out to, get on the radio and talk to a team like the Probe 1 team and say, Probe 1 digits, and Probe 1 would reply with the degrees and tenths of degree of their position, lat and lon, back over the radio, and the field coordinator would type those in on a keypad, and then their icon would move on the screen. So really cool, but pretty primitive. Mobile mesonets were invented for Vortex 94 and 95 and developed here in Norman at NSSL with CIMMS support. These were sedans with weather instruments on the top and steering columns that smoked and were recalled during the experiment, actually. The airborne Doppler had been developed I believe in the late 80s or mid 80s, but one of the new things that happened around Vortex 94, 95 was a tail radar on this aircraft that could look both forward and backwards at slightly different angles. So they could essentially do dual Doppler as they flew along. They wouldn't have to do one leg in one direction and then do a perpendicular leg to measure the airflow in the storm. First mobile Doppler radar, this is Dow 1, was developed here in Norman with support from NSSL and CIMMS, and this obviously took off. This concept took off then over the next few years with a number of mobile Doppler radars being developed for mobile research. And there's the NOAA P3 aircraft with a belly radar and tail radar. So all those things happened in Vortex 94, 95. So the science, we did, that was a hypothesis-driven experiment by design. Our hypotheses were great for leading us to make important observations. They weren't really testable and refutable because we would have needed to see, dozens of storms to get a decent sample to test those hypotheses. And we haven't seen dozens of good storms in 20 years since that experiment. But it was the hypothesis drove the experiment well. It wasn't terribly successful because when we looked at the data afterwards, we found out that tornadic storms and non-tornadic supercells looked a lot alike, at least in the kind of data we were collecting. But that's important to know because then that gives you information to design your next attack on the storms and collect data different than what you collected in the last experiment. MEPRS, the MCS electrification and polarization radar study. The ballooning to measure electric fields and charge in storms was pioneered here in the 1980s. And with time, we started to develop these simple models of the charge regions in thunderstorms. These models got a little bit more complex as more observations came in. MEPRS things started changing then because we applied an airborne Doppler radar, dual Doppler radar, and also sounding, the electrification soundings, as well as, for the first time, polarization radar, if I remember right. I hope I don't have these confused. I might be thinking of a later program, but the point is that we went from this concept of a simple single sounding through a storm to measure charge to multiple soundings in the context of airborne Doppler data to get a better understanding of how the charge evolves in the storm. A little anecdote is back in the 80s, I was working with Dave Rust on one of the mobile platforms, and my job, this was a great job to have for hours and hours on end, is every time I saw a lightning flash near the vehicle, I pressed a little button on the end of a wire, and it made a mark on their record so we knew that a lightning had occurred near the vehicle. I think that went on until one day I let that device drag on the pavement next to the van after I jumped in when the tornado happened, and multiple little marks and then nothing. A similar electrification study then was STEPS, which happened in the high plains. Northwest Kansas is where it was centered, with 3 ground-based Doppler radars instead of airborne radars, and mobile ballooning and mobile MES network. And this one actually, instead of looking at MCS, the big convective systems, the squall lines, this one was looking at isolated storms, such as the supercell in the upper left, which was more of a classic storm, and the one in the lower left, which was a low precipitation or one of the drier type storms that happen in that part of the country. The International H2O project, which that pancake house was named after this, happened in 2002. And the main involvement from Norman was in convection initiation. We actually had 9 mobile mesonets. Again, the platforms that were developed for the first Vortex became a part of IHOP in 2002. We had mobile soundings. There were aircraft from NCAR, and we had mobile Dopplers. I think I might have mentioned that. Something that's on this picture that didn't happen is that UAV flight in the middle, which would have been wonderful to document the character of a dry line right above the ground or a boundary that might initiate a storm. That was a great plan, but about during the middle of the planning of this experiment, 9/11 happened, and the FAA said there will be no more UAV flights in the U.S., and it has actually taken now it's taken at least 15 years to even get primitive UAV sampling of these types of features going again because of that event. Telex, thunderstorm electrification and lightning. This is the one I was thinking of earlier. This one actually started involving dual polarization radar as well as lightning mapping arrays to understand how the electrification happens and how that's related to the lightning that occurs both at the ground and aloft, as well as the types of particles that are in the storm in terms of the raindrops, hailstones, snowflakes, the cloud droplets, all of these things, how all those things are tied together to develop the electrification in the storms. So as you see, we moved from basically in the 1980s, a few instruments being deployed one at a time, just learning what these instruments do and how to deploy them, to now multiple instruments in mobile settings to get the bigger picture of what's going on in the atmosphere. Vortex 2, 2009 and 10. Boy, this was a beast. My memories of this experiment aren't terribly fond, but some of the new things we tried in this one, well, we had new science ideas that basically grew out of Vortex 1. But in this case, we had several more mobile Doppler radars of different wavelengths, different bands, different scanning strategies, same mobile mesonet type instruments, and a lot of mobile ballooning. And I think from Vortex 2, this is, of course, a multi-agency, multi-university, but with a lot of CIMMS involvement. Vortex 2, I think, again, it was another experiment where we probably discovered more that we weren't observing quite right and quite where we needed to observe to answer the questions we were asking. And so that's important information, and that's influencing the evolution of another experiment I'll talk about in just a second. This is kind of a cool thing that's been developed here in Norman, the Videosonde balloon-borne particle imager. That's it on the right, sitting on a laundry basket, so you get a sense of how big this thing is. It's basically like that. It's got a video camera in one end and a dark mat and lights in the other end, and it takes continuous images of the particles in the storm as it ascends through them as far as it will go, and then that imagery is recovered and analyzed in software to find out how big the particles were, how many there were, and all of that sort of thing. Again, really important information in terms of understanding the electrification of storms. The DC3 experiment, deep convective clouds and chemistry. I'm not sure how much involvement we had here, but this one looked at how the atmospheric chemistry changes as air moves from the inflow of the storms near the ground up through the storms and then is ejected into the upper troposphere or even the lower part of the stratosphere. How do the chemical changes occur as the air moves through the storms? That was the emphasis here. MPEX, the mesoscale predictability experiment. The idea here is in the morning we take a jet and drop a number of drop sondes in an area where it looks like our forecast models may be sensitive to getting more and better observations. So that's these yellow wind flags out there over Colorado and New Mexico. And then so the forecast models are run, and then in the afternoon, as storms are beginning to occur, there's several more surface sounding systems that try to measure the environment right around the storm and see if those observations are helpful in forecasting the evolution of the storm. Now, MPEX is going on, ongoing through the work of Mike Caniglio and others here, to continue looking at the sensitivity of supercells to the environments in the near neighborhood, and that'll flow into the Taurus program I'm going to talk about here in just a second. planes elevated convection at night. This was, I didn't get to participate in this, but I'm not brokenhearted about that because sitting up all night with a radar or a balloon vehicle waiting for storms to come and hammer me at 3 in the morning is just, well, but it's a big problem. We've always been decent at forecasting afternoon storms and evening storms, but these storms that form during the night are a whole lot less predictable, and the mechanisms for their initiation are less well understood. So that's what Pecan gave us. My clock agrees with you, by the way. Vortex Southeast. There's probably many of you may not know about this experiment. This is a fairly large endeavor that has been going on since 2015. I don't know why I said 16 there, typo. So Vortex Southeast right now is administering about $15 to $20 million worth of research. And the problem in the Southeast is that the meteorology is much less well understood than the plains. The things that happen in the environment that help promote tornadogenesis are not quite like what we've been looking at in the plains for 20 years. But on top of that, there's all sorts of issues with the way people perceive warnings, the way they receive them, the way they respond to them. So big bunches of social and behavioral issues as well as operational issues. So we're trying to look at all those things in Vortex Southeast. But there is a field campaign component, and the one that's going on right now we're calling MESO 1819. We have a special sounding network that's going to be activated and do 6-hourly soundings whenever it appears there will be severe weather in the Southeast, all the way from now until April. And then nested within that northern Alabama region will be several more sounding systems, 3 or 4 profilers and mobile Dopplers and so on. So we're going to try to see if we can improve. There's a real-time HER assimilation experiment going on with this. We're going to try to see if we can improve operational HER forecasts of the convection initiation, behavior, evolution, and structure in the Southeast and the tornado potential through these special observations. All right. Finally, this is sort of a new portfolio brought to CIMMS by Greg McFarquhar when he took over the directorship. And this is studies of clouds and aerosols. Aerosols are the tiny little particles that cloud droplets can form on, and how those things interact. One of the experiments they're working on, Oracles, is taking place. It took place in Namibia in 2016, looking at how the aerosols generated by biomass burning in Western Africa actually influence the clouds and the behavior of the clouds there. So these kinds of questions are very important for climate change studies and understanding what the influences of man are versus what would go on naturally in the absence of man's effects. And so if you have questions about this new thrust, I think you should get together with Greg. You probably have some interesting stories. Lastly, back to supercells. You've seen the animations probably with this little river of vorticity that happens in the storm. This is an area of spin, both horizontal and vertical. It starts in the rainy part of the storm, moves toward the updraft, gets turned upward, and develops what will become tornadic rotation. We don't even know if that thing is there in real life. The models show it, but it's never been observed. We don't know how it gets there, so we're going to the field again in an experiment called Taurus with UAVs, mobile mesonettes, mobile Dopplers, sounding balloons, and try to understand that. So I want to make a little editorial comment now that Greg's approaching. No, you cannot have the microphone. Something I've seen over my 40 years, I think probably first noticed in some of the more prominent researchers in this field, is that they tend to combine disciplines and approaches, for example, modeling, observing, working with operational folks, social and behavioral science. Individuals have been combining that and been very successful. I think that's a nice paradigm for where field experiments are going to go in the future. Combinations of a number of disciplines working together. Actually, not just this sort of hopscotch evolution thing where models discover something, observers go check it out, modelers discover something, but actually everyone working together simultaneously to advance the knowledge. And then my final comment is that when I look around at CIMMS, there's a whole lot of really good field observing talent, even in this room. And so I hope that we'll continue to expand our role in the area field campaigns going forward.
Thank you very much. We have time for a question or two. Yes, Barian.
That was a very nice talk. Going to Vortex Southeast, Russ Schneider, in his lecture yesterday, spoke about some of the challenges of forecasting tornadic activity in that particular region, given the proximity of the Gulf and so forth. In your field program, do you have, what accommodations are you making for that, or how do you recognize that additional complexity? Not to get into the social sides, which I know we're going to hear from now, but could you speak to that at all?
Yeah, so in particular about the Gulf, we're having, it's a difficult forecast problem because a number of our observing campaigns have been hampered by the fact that storms form right on the Gulf Coast and they weren't expected. There's not a whole lot we can do yet in Vortex Southeast about improving our observations over the Gulf of Mexico and understanding the air masses that are on their way toward the continent. So that remains a big challenge. Other big challenges are the storms in the southeast can form with very little cape, which is the buoyant energy that feeds the storms, when the shear is huge. So that's different than the southeast, or different than the plains. And that is something we're doing a lot about with detailed observations of the lower part of the atmosphere.
Okay, one last, Harold.
I can't turn Harold down.
Okay, looking forward to the future. I recall back in about 1991 at the Tornado Symposium when a group of us thought that we needed to do a field project to look at things. And that same group of us decided that we needed to hire you to...
Mistake.
Yeah, well... Yeah, we can talk about that. And that you should be the field coordinator. And then 15 years after that was Vortex 2. So that means Vortex 3 should be 2024, 2025. Have you started pre-planning for your role as field coordinator in Vortex 3?
Yeah, my plan is to retire before that happens.
Okay, well, thank you very much. We should probably move along. Okay. Our next talk will be given by Dr. Kim Klockow-McLean, and she is a research scientist and societal applications coordinator for CIMMS, and she serves as the group lead for the newly formed Societal Impacts Group. Before joining CIMMS, she worked for several years as a policy advisor for social scientific research at the NOAA Office of Weather and Air Quality outside Washington, D.C., where she served as the first social scientist in that office. She was the 2013-14 AMS UCAR Congressional Science Fellow, and she also completed her PhD in Human Hazards Geography from the University of Oklahoma. She also holds an MS in Professional Meteorology from OU and a BS in Economics and Synoptic Meteorology from Purdue University.
Thank you, Greg. All right, well now for something a little bit different, although the seeds of this have been woven through many different presentations. So I'm really excited to talk about the societal impacts portfolio of CIMMS today. And much like others have said, especially Adam, I haven't been here to witness the last 40 years of CIMMS development, but I have you beat a little bit. I am the youngest of the presenters. I was actually -4 or 5 years old when CIMMS was created. So I sat down with Randy Pepler and asked him, okay, what have I not been there for? Give me some insights. But fortunately, it turns out this is a really recent portfolio, and I've been there for a lot of the kinds of big turns and development of the societal impacts portfolio of CIMMS. Kind of like Forrest Gump, you know, how he was there just incidentally in really interesting places throughout history. I feel like as I was putting this presentation together, that's kind of how I was through some of the development of CIMMS. So in the beginning, the first vestige of the societal impacts portfolio I could find was in 1993, the end-of-year report. And at the time, the theme was called Socioeconomic Impacts of Mesoscale Weather Systems, that first part makes sense for CIMMS, and regional scale climate variations, which you might look at and say, that makes a little less sense for a place like CIMMS. So I'll draw your attention to the socioeconomic part and the regional scale climate variations part, and describe how both of them came to be. Really, the reason that this existed was Pete Lamb. And he made this whole theme really come to life. He came here in 1991, so it didn't take him very long to establish this as one of the CIMMS research themes. And much like Greg, he came from the University of Illinois, but with a slightly different group. He was with the Illinois Water Survey. And the Illinois Water Survey, a place that actually brought a lot of people here, they had done some really important work valuing climate observations and climate forecasts for agriculture. So some of the preeminent work that's been done in that area came out of folks who worked in the Illinois Water Survey. And so Pete himself, he did research examining teleconnections between global scale forces and the kinds of weather patterns that favor or don't favor agricultural production. So when he came here, he carried that research with him and continued to work in that arena. And I'll also through this talk suggest, I'm kind of giving like a history of social science talk a little bit. And CIMMS, the changes that have gone on through CIMMS have actually been reflected in the changes going on in our field as a whole as we've worked to embrace the social sciences and figure out even what social sciences we need. So it all started with economics. And so Pete was working with folks who were doing economics work, and NOAA as a whole was really involving itself with economics. It actually had been involved with economics from the beginning, from the 1970s when it was formed as an agency when we brought fisheries under the hood with weather, because fisheries, they have treaty obligations that they have authority over, and so economic milestones are part of that. Economists have always worked on the fisheries side. They have a very robust economic capability. We also needed economists. Anytime that you guys wanted to get those toys, you know, that you were all talking about, the different radars and observation systems, you would go to Congress and present an economic benefits case. So economists were really useful for that too. Within about 10 years of Pete arriving, CIMMS had involved itself with some local economists to do a different kind of work. On the left is Dan Sutter. He was an economist here at the University of Oklahoma for a number of years. He came from hazards insurance, was sort of his area, the way that he got hooked in. And then in the middle is Kevin Simmons. He was at UCO at the time, and he came to us studying hazards mitigation policy on the benefits of mitigating. So those two teamed up, and they wrote eventually a book that many of you are familiar with, The Economic and Societal Benefits of Tornadoes. They conducted a big econometric analysis trying to figure out what are some of the factors that belie fatalities in situations where there are tornadoes. And on the far right side, we have Jeff Lazo. He wasn't here, but his work has been very influential in our field as well. He's valued the economic impact of weather forecasts on the U.S. economy and was very influential in helping us to get some of the things that we've gotten as a field. So, interestingly enough, I'll start with the economists. By the mid-2000s was sort of this feeling that economics was getting us some of the questions that we wanted answered, but it wasn't doing a lot of what we wanted to see. We were really interested in questions like, why is it that people are dying and what can we do about it? Those big models that the economists were giving us helped us to define some of the factors that people exhibited that led to or predicted that they might be more likely to die in a tornado, but it didn't help us to go further than that. And for that, we needed more social scientific input than that economists alone could provide. Jeff Lazo was at NCAR at the time, and he recognized this and was also very interested in these broader questions. And so he teamed up with folks like Rebecca Morse and Julie Demuth, who many of you know. At the time, they were just trained as physical scientists. They later then got trained in various aspects of social sciences, but they teamed up to create what became WAS-IS, that was funded through NOAA, a 5-year investment at NCAR. And this was a turning point for the careers of many people. Many people in this room actually went through WAS-IS. Raise your hand if you went through WAS-IS or attended a WAS-IS meeting at any point. A lot of people. And I mean, this is one of the reasons why I don't have pictures actually of all the people in the room who do societal impacts work, because it is a large fraction of the people here who were influenced, beginning with especially this particular program. So eventually we decided that we wanted to bring what they had at NCAR, what they're developing there, we wanted to develop that closer to home and have a really well-honed research capability in the social sciences. So in 2008, A 3-year program was launched involving Eve Gruntfest, who was one of the original progenitors of Was-Is, and she brought on postdoc Heather Lazarus. These two folks, they come from a field of, I would qualify it as sort of the natural hazards and disaster sciences community. That's a community of social scientists who study how people manage to live, adapt, survive in this very volatile world. And Eve comes from hazards geography in particular. She was a student of Gilbert White, who he was this really famous geographer who helped to describe how when we try to control floods and prevent flood threat from impinging upon us, we actually increase our overall risk by building things like dams and levees and so on. And if you look around the country at the natural hazard centers and disaster centers, many of them are populated by students of Gilbert White. He was a very influential man. Eve herself studied how people respond to floods and the kind of counterintuitive ideas people have about how they should proceed to survive them that actually end up getting them killed. And then Heather Lazarus came to us from the field of anthropology, studying climate change adaptation. So through the 3 years of social science woven into meteorology, or SWIM, 2 master's students graduated. Both went through the geography program. And they had 3 PhD students. I had been one of them. Gina Esco was another, many of you are familiar with, in communication, and Monica Zappa. And all 3 of us, for various reasons, ended up leaving the program, so we didn't graduate from SWIM per se. I think the coolest of the 3 of us is actually Monica Zappa. It might not be a name many of you are familiar with, but she one day got on her bike, biked up to Alaska, joined a fishing village, and raises Iditarod dogs. And actually now, every year, she runs the Iditarod. So as much as she left the field, she went on to do something really stinking cool, and we're still really proud of her for it. Love seeing her pictures every year. So by the end of that 3 years, Eve retired. SWIM as an organization sort of sank, but social sciences yet persisted. In large part because of some of the other social scientists who were on campus who did related work, but were part of a different community. This is actually folks who are part of the risk community. So these are people who study a broader class of risks, not just natural hazards, but any of the risks that people can find themselves facing. And on the left, Dan O'Hare, he was the chair of the communication program at the time. And he came to the university studying, he had big NIH grants, and he studied smoking campaigns and why it is that people, though they know that smoking will kill them, why do they persist in smoking? Especially experts, actually. Why is it that they in particular continue to do this? On the right, the right 3 are all political science faculty here at the university. Carol and Hank came to us having done a lot of work for the Department of Energy, and they have studied nuclear energy and how we make choices about disposing of the nuclear waste that results from nuclear energy. So all of these folks came from different kinds of risks into weather and climate. Dan O'Hare was really interested in weather risk issues, and he led a number of efforts that brought people from across campus to do systematic reviews of literature that could apply to weather. And Carol, Hank, and Joe were really interested, initially they were really interested in climate change and climate policy and how it is that people make decisions for dealing with climate change or failing to do so. And I had the opportunity to do research with all of these folks in my PhD years. Also at the same time, there was another undercurrent of social scientists or behavioral scientists coming through the Weather Center. We had folks from an applied branch of psychology, human factors researchers. Chen Ling was actually here at the university. Robert Hoffman was not, but he had done a lot of work with the FAA in studying pilot behavior and how they used weather instruments. So human factors researchers are people who explore the human-machine mix and how we make tools that humans can actually use to do the things they need to do. These folks helped to inform a thread of research that several people have mentioned, that of the human forecaster. So we're creating all these technologies. Can people use them? How do people use them? How does the forecaster use them? How can we make them so that they are more usable by the forecaster? All of that was going on at the same time. So you can imagine that among all of this milieu, there were so many different theoretical frameworks coming in. It's kind of like putting it in a physical science frame, it's kind of like having chemists and biologists and physicists all come together wanting to study, maybe molecular behavior or something. And they all come at sort of the same item, but with very different ideas about how it functions, and very different languages, and very different kinds of methodologies for exploring that. And while we all involve ourselves with people, I can't tell you in these years how volatile it was to try to have conversations about, okay, so what is the research that needs to be done in the weather community to try to save lives? What of all these questions that everybody is studying are the most important, and how is it that we can all come together and get this research conducted? These were really exciting, interesting, but also very challenging years. One of the neat things I want to highlight that grew out of this, though, actually, there are folks who were here sort of in this building who decided to change their career trajectories mid-career and pursue more of the social behavioral scientific work, and then go on to influence one of our native departments, the geography department, and create sort of a hazards geography capability where one didn't really exist before. Randy Pepler, our own Randy Pepler, he ended up getting his PhD in geography, in very human, very like almost quasi-anthropological geography. And Renee McPherson had been my advisor, my master's and PhD advisor, and I kind of feel like we had a Gilmore Girls thing going where you lead, I will follow. I joined the geography department for my PhD, and eventually Renee joined it as faculty some years later. And Mark Schaefer got his PhD in political science, was studying adaptation policy, climate change adaptation policy kinds of questions, and also has joined the geography department. So where's CIMMS going now? We evolved after all of this, in the German you say the Sturm und Drang, all of the drama of trying to bring all of these groups together and move on from economics and grow our social scientific portfolio and think about what we needed to be. The theme changed. The theme no longer was socioeconomic and including climate issues. It became societal, a broader term that they meant to encompass all of these other sciences, and socioeconomic impacts of high-impact weather systems. And it's no coincidence that that happened in 2012, because in 2012, also within NOAA, there was a keen focus growing on social sciences for a weather-ready nation. After the 2011 tornadoes, there were a series of workshops held to try to figure out, well, what went wrong? Why did those people die? The first questions and assumptions were all about physical science, and coming out of those meetings, it actually was revealed that probably the issues are social scientific, and we need communication scholars, we need behavioral scientists of a bunch of different forms to really inform how this works. So sometime after the Weather Ready Nation became a major NOAA priority, it became reflected in the CIMMS research theme, and NOAA headquarters started to put out more literature on this. So this is actually a report that's available to anyone who wants to see more of the work that's relevant in this area. It was put out just a couple of years ago. I got to be one of the report authors because, again, incidentally, I just happened to be at headquarters when they were really trying to put this together. So this is a really neat generic overview of a lot of major theories and ideas that encompass the work that we're doing here. And here at the university, one program really stands out as having brought together all of these social scientific perspectives, as well as some of the physical science development work that's going on into an end-to-end cohesive package, and that's Facets, that sort of Lance's vision, bringing us all together. So I'll conclude by just saying our research portfolio today has become very holistic. It's system-oriented. We examine all of these questions. We look at the human forecaster, how it is that they take in technologies and then communicate information downstream, how that information is used by our partners, and then how the U.S. population responds to it as an end-to-end system. And with that, I'll take any questions. Thank you.
Questions? I guess you did a pretty good job. You've talked mainly a lot about, what about climate? Do you want to say anything about societal aspects of climate?
It's an interesting question. Since Pete left, we kind of grew away from that a bit. But I mentioned Heather Lazarus, the swim postdoc. She left. She went to she went to Boulder, but she still does work with the South Central Climate Science Center. And I think that this work continues, but maybe just not in this institute, but in our other related institutes. As I look at Renee, to nod or no, I think that that's where a lot of that social scientific work has gone. It's not that it left the university, but it just was housed in a different institution.
Okay, well, thank you very much. Okay, I promise I will be brief because apparently there is a poster session and I want to make sure that everybody gets time to go see the posters. And I'm sure that's not a motivation that there is free food out there, but there is also food starting in a couple minutes. So what I would like to talk about is the future of CIMMS. And I think the important thing is we're going to want to maintain the strengths of CIMMS. That's always something that's very important. We've heard a lot about projects today that are going on but haven't been finished. Facets, MRMS, Warn-On Forecast, radar engineering, radar meteorology. There's a lot that's going on there. We have a lot of highly talented people in CIMMS. They're working on projects in collaboration, of course, with our NOAA partners. And this work is going to continue and will be a major focus of CIMMS in the near future. So what I want to talk a little bit about is acknowledging that we're going to continue with these research foci. And this is, I think, Jeff, you put these research foci up in your slide. That is going to continue. So the question is, should we be doing anything that goes beyond that? And I have a couple ideas I want to propose and just think that these are things that we can work forward towards in the future. I think in addition to some of the work we're doing here, I think that we have to expand and think about other high-impact weather events. So what are potential national threats in coming years? I think if we think about economic damage and societal impacts, heat waves and droughts are two very important areas that, we maybe don't have a lot of work going on here in CIMMS, but I think that these are things that will continue to grow in importance in the future. Landfalling hurricanes, I think, is another very important aspect. If we've taken a look, somebody showed sort of the umbrella plots of hurricane forecasts, and they get a lot of attention as they're going towards land. And then the story is really only half over once they make landfall, because some of these storms, they'll make landfall and they'll move quite quickly. Others will not move very quickly, and there will be huge amounts of precipitation associated with them after landfall, and there will be a lot of inland problems associated with landfalling hurricanes. Snowstorms. Tomorrow, I think there's going to be a nice weather event on the East Coast of the United States. And, I think there's still a lot that needs to be known about snowstorms. So, for example, myself and some collaborators will be doing a project funded by NASA looking at nor'easters in the coming years. And I think this is something that, I think I'd like to see become, and I know there's a lot of other work going on in snowstorms here too as well, but I think that's a coming focus. Floods, hydrometeorology, there's a lot of work going on here on that right now. I think we need to expand on that. Tornadoes, especially in the southeast, we've talked a bit about them, learning more about that, learning more about the lead time, reducing false alarm ratios. This obviously impacts Warn-On Forecast as well. And then talking about frequency of extreme events and changing climate. Are nor'easters getting more frequent? I was asked that question last week when I gave a seminar, and I think it's a very difficult question to answer from a strictly observational perspective when the frequency of these events isn't that great to begin with. Important applications. I'm glad, Adam, you mentioned seasonal to subseasonal forecasts. We had a workshop here a couple months ago where we had a lot of military from around Oklahoma come. And, in terms of long-term climate, they acknowledged its importance, but from their perspective, what they were interested in really was seasonal to subseasonal forecasts, because that affects their planning in the coming year. Is a city going to need a lot of salt for plowing their roads? Is a military base going to have to worry about a lot of really high temperature days or, droughts? That's what they're going to worry about. Then, of course, worn-on forecasts, probabilistic forecasts, we've talked about that. Socioeconomic aspects of high-impact weather. And then I don't think we can forget about the Arctic. The Arctic is the area of the Earth right now that is changing most due to climate change. Will that affect the continental United States and the weather patterns we get here? And do we also have to think about forecasting for the Arctic? If the the Northwest Passage is used for shipping over the coming years when it's not sure how long it's going to take to be ice-free, I think inevitably economic aspects may trump environmental aspects, so we may need to worry about seasonal forecasts in the Arctic. In terms of strategic goals, I think again it was you, Adam, made the point that in a lot of your earlier slides, you pretty much exclusively had males. And it's good that we're getting a much better gender diversity. However, I think there's other aspects of diversity when I look around the room that I think that there are other underrepresented groups that we haven't done a good job in yet attracting to CIMMS. And I think that's something we have to work on in the coming years, is to continue to increase our diversity. We have a lot of educational activities on within CIMMS with the incredible number of our faculty, the incredible number of CIMMS scientists who serve as adjunct faculty in the School of Meteorology. But I think we can, and we have a lot of students too, but I think we may be even able to further increase that as CIMMS continues to grow and expand. One thing that we did last year is we established the Peter Lamb Postdoctoral Fellowship. Cassandra Shivers-Williams was our first winner, and she's right there. We're going to be advertising shortly for our second postdoctoral fellow, and I think this is a way, we named it after Peter Lamb, because it's a way sort of acknowledging his legacy and his role in educational activities. The other thing we're trying to do is we're trying to hold more symposium, brainstorming sessions on important topics to address, to try and identify pressing science issues and what we need to do in order to have a strategy for addressing those science issues so that when funding comes available for that, we'll have a strategy. If there's a new initiative from NSF or NASA that may expand upon the work, we can leverage our NOAA resources if we're ready with how to address these proposals. And this should include a major societal aspect as well. So our first one we held a couple weeks ago, Uncertainty. I won't read the whole title, but it was basically uncertainty in everything and how it impacts predictability of weather. Next year, I think we'll try and look at landfalling tropical cyclones and Arctic weather, and also looking at impacts of Arctic weather on lower latitude weather systems. Hydrometeorology and hydrology will be another, and then I think seasonal to subseasonal forecasts will continue to be more important. Eric talked a lot about field programs. There's multiple ideas. We could go even further than that, but I really think we should work on trying to get more and more of that going. And part of these field projects, there can be lots of student opportunities. Here we are in Sao Tome with some of our students in front of the NASA P-3 aircraft. This is the Cloud Group. Sorry, Jens, I didn't put your team on here. But another thing I really think that we should look at is international collaborations. I really think we want to enhance the stature and reputation of CIMMS around the world, and also to both give our expertise to foreign partners, but also gain from the expertise that exists with foreign partners. We really need more collaboration there. So last week, myself and my research scientist, we were in Beijing, talking to a number of partners in China, and there was a lot of interest. They had huge interest there in trying to reinvigorate a U.S.-China Memorandum of Understanding on cooperative research on major disastrous weather and climate events that existed that sort of aged off. There was also, we could enhance collaborations with the Korean Meteorological Administration. We've been working with CAPS on that, and I think there's a lot of expertise in Korea, and I think there'd be a lot of activities there. The Finnish Meteorological Institution has wanted to collaborate us. We're going to have a visitor from Ireland coming. So there's a lot of interest there, and I think here we can really enhance our visitor program to CIMMS. We've had recent visitors from Korea, China, and Israel, and there's other countries too who want to come. So I think that will really be a growing area of interest too. And I think I'll skip the last few slides I had, which were more on the grand challenges, some nice pictures. So in the interest of time, I'll see if there's any couple quick questions, but we'll also want to move on to the poster session soon, so that there's lots of CIMMS scientists who've done a lot of really good work, and I want to make sure there's plenty of time for them to show their results. Thank you. Steve.
So, in a sense, I've been connected with CIMMS for 40 years. Like I said, being one of the first 3 employees of CIMMS, now the director of NSSL, now retiring. And M is still the center part of the acronym CIMMS, C-I-M-M-S. And when I started research with Carrie Emanuel, Carrie at the time was studying conditional symmetric instability, and I was studying gravity waves. These are mesoscale phenomena. Over the years, the past 40 years, and this has been a tremendous outpouring of research creativity on the part of CIMMS employees and students supported by CIMMS for 4 decades. The emphasis has shifted from mesoscale to convective scale. The emphasis has shifted from studying of processes so much to studying of predictability and improvements in warning and forecast skill, and developing tools for observing what needs to be studied to improve that. That's just my perception. I know Eric and I have talked a little bit about this passion that I have for, do we need to put a restored emphasis on mesoscale? That's the question. Now, I agree with everything you just said here at the end, but for example, looking at the posters, I can count 2 or 3 at the most that really are looking at mesoscale processes out of several dozen posters. Now, is that a warning sign, or is it saying, no, the things have changed because the technology's improved, the model resolution has improved, like Adam said, we're at the CAM scale now? Is it just because we have such sophisticated capability that the emphasis on process studies at the mesoscale has taken a bit of a back seat to that? What's your take on that, Greg, in terms of the next 40 years?
Okay, well, I think really, I'll give a bit of a brief answer so we can get to the poster session, but I think really it's going to be multi-scale and multi-scale interactions, which is what we really need to have an impact. And it's partly because we're able to resolve features that couldn't be resolved as well for 40 years ago. So I think mesoscale will continue to be a part and plays a role, but I really think we're expanding more to multi-scale so that we can get lots of different interactions going. So that would be my very quick answer to your question. And with that, I think if anybody has any other questions, I think we'll save them for the poster session so that the presenters can get out there. So enjoy the poster session. And I thank you very much, and I'd like to also really thank the speakers who all gave outstanding talks. Thank you very much.